Hello there, and welcome to Just About Earth, a place where curiosity settles in like a warm blanket and science takes the long, gentle road instead of the fast, noisy one. Tonight we're not rushing anywhere, we're drifting. We're floating above a sea that looks familiar on the map, one that touches 3 continents, hosts busy ports, and carries ferries, fishing boats, and vacation dreams across its surface. But for a very long time in the deep past, this sea did something so strange, so unexpected, that even the planet itself seemed to pause and watch. It disappeared. Not just for a moment, not for a season, but for hundreds of thousands of years, leaving behind a vast, silent basin where water once shimmered and waves once whispered against stone. Before we wander into that vanished world, let me ask you something simple and human. Where are you listening from right now? Is it late evening, early morning, or somewhere in between, that quiet hour when the world feels softer and sounds seem to travel a little farther? Are you curled up under a blanket, sitting at a desk with a lamp glowing nearby, or perhaps lying back and letting the ceiling become your personal sky? Wherever you are, whatever time it happens to be in your corner of the world, I am glad you are here, sharing this small moment in a much larger story. If this gentle journey through Earth's past feels calming or quietly fascinating, and if you find yourself enjoying these slow walks through deep time, you might consider giving the video a like or subscribing. It helps this little space reach other listeners who may also be looking for a peaceful way to unwind while learning something about the world beneath their feet. There is no rush though. For now, let's just breathe, settle in, and allow the story to unfold at its own pace. Imagine for a moment standing on the edge of the modern Mediterranean. Perhaps you picture a familiar scene. Blue water stretching toward the horizon, sunlight scattering across the surface in shifting patterns, the faint sound of waves rolling onto a beach made of sand, pebbles, or warm stone. You might see cliffs rising along the coast, dotted with small towns, ancient ruins, or winding roads that cling to the landscape as if they have learned its shape by heart. It feels timeless, as though this sea has always been here and always will be. But Earth, as it turns out, is not very fond of always. It prefers change. Sometimes that change is slow and almost polite, like a coastline that creeps forward or retreats by a few steps over thousands of years. Other times, it is dramatic, sweeping, and so large in scale that it reshapes entire regions of the planet in one long, drawn-out motion. The story of the Mediterranean disappearing belongs firmly in that second category. We're going back several million years to a time when the world looked both familiar and strange. The continents were already close to where they are today, but the details were different. The climate was warmer in many places, forests grew where grasslands now stretch, and animals roamed that would feel both recognisable and oddly out of place to modern eyes. Early ancestors of humans were beginning their long, complicated journey, though they had no idea what lay ahead, and certainly no idea that beneath their future homelands, entire seas would one day come and go. The Mediterranean at that time was not just a sea, it was a connection, a meeting place between the Atlantic Ocean and the vast basin carved into the land between Europe, Africa, and what we now call the Middle East. Water flowed in through narrow gateways, filling the basin and keeping it alive with currents, salt, and the countless forms of life that thrive in moving, breathing seas. Now, try to picture that connection slowly tightening, like a door that is being gently, almost politely, pushed toward its frame. No one notices at first. The water still moves, the tides still rise and fall, fish still swim, and waves still reach the shore, but deep below the surface the planet is shifting. Tectonic plates, those enormous slabs of Earth's crust that move so slowly we rarely think about them, are pressing and sliding against one another. Land is rising in some places, sinking in others, and the narrow passages that link one body of water to another are becoming shallower, narrower, more fragile. This is where the story begins to lean forward. The Mediterranean is a basin, which means it sits lower than much of the surrounding land. It relies on water flowing in to replace what is lost to evaporation, and in warm, dry climates, evaporation can be a powerful force. Every day, under the sun's steady attention, water lifts into the air and drifts away as invisible vapour, leaving salt behind. Normally, rivers and ocean currents bring in fresh water and dissolved salts to keep everything in balance. But what happens when that balance starts to tip? Think about a shallow puddle on a warm day. At first, it looks like any other patch of water reflecting the sky. Then, hour by hour, it shrinks. The edges pull back, the centre becomes thinner. Eventually it vanishes, leaving behind a faint outline of dust, minerals, or dried mud. Now, take that simple everyday process and stretch it across a sea that spans thousands of kilometres. Give it hundreds of thousands of years instead of a single afternoon. That is the scale we're working with here. As the gateways between the Mediterranean and the Atlantic began to close, less water flowed in. Evaporation kept doing what it always does, quietly lifting water into the sky. Rivers still poured in from surrounding lands, but their contribution was not enough to make up for what was being lost. Slowly, almost imperceptibly at first, the sea level began to drop. Along the coasts, beaches extended farther out. Cliffs found themselves overlooking dry land instead of water. Harbours turned into shallow bays, then into wide, open plains of damp, salty ground. Life in the water felt the change long before any distant observer might have noticed. Creatures adapted to open seas found themselves trapped in shrinking, increasingly salty pockets. Some perished. Others retreated to deeper areas, following the last remaining pools of liquid life. Above the basin, the air itself may have changed. With less water below, the region could have become hotter and drier. Winds might have carried fine salt dust across the surrounding lands, settling on plants, soil, and anything else that stood still long enough to receive it. Rain, when it fell, would have washed that salt back toward the low points, feeding the growing layers of minerals on the basin floor. If you were somehow able to stand at the centre of this disappearing sea during that time, you would not be looking at a simple, empty hole in the ground. You would see a vast landscape shaped by water that had once been there, and by salt that refused to leave. There would be deep valleys carved by rivers that now had to flow down into a much lower basin, cutting dramatic channels through rock as they rushed toward the last remaining pools. There would be flat, blindingly bright plains where salt crystals covered the ground, reflecting sunlight so intensely that the horizon might shimmer like a mirage. It is tempting to think of this as a sudden event, like a plug being pulled from a bathtub, but the reality was far more drawn out, more patient, more in line with the planet's usual way of doing things. The Mediterranean did not vanish overnight. It withdrew, paused, reshaped itself, and withdrew again. At times, it may have partially refilled, only to lose the water once more. The story is not a straight line, but a long winding path marked by shifts, adjustments, and slow transformations. Scientists call this period the Messinian Salinity Crisis, a name that sounds technical and distant, but at its heart it describes something very simple. A sea became too salty to sustain itself. It lost more water than it gained, and in doing so it revealed the quiet power of evaporation, gravity, and the restless movement of Earth's crust. What we know about this vanished sea does not come from a single dramatic discovery or one perfectly preserved snapshot of the past. It comes from layers of evidence stacked like pages in a very old book. Deep beneath the modern Mediterranean, drilling projects have pulled up cores of rock and sediment that tell a remarkable story. In those layers, scientists found enormous deposits of salt, gypsum, and other minerals that only form when seawater evaporates in large quantities. Not just thin streaks or scattered patches, but massive, thick layers that point to a basin that dried again and again over a long stretch of time. These salt layers are not just geological curiosities, they are records. Each one marks a period when water receded and minerals settled out of solution, building quiet, invisible mountains beneath what would later become a refilled sea. Today, those buried salt formations influence everything from the shape of the seafloor to the way oil and gas move through underground rock. The past, even when it's hidden, still has a hand in the present. As you listen, you might start to feel the scale of this story pressing gently against the edges of everyday thinking. We're used to measuring time in hours, days, and years. Even a decade can feel like a long stretch. But here, we're talking about hundreds of thousands of years, about landscapes changing so slowly that no single generation of living creatures would ever notice the full sweep of what was happening. It is a reminder that the world we see is not a fixed stage, but a moving one, constantly being rearranged behind the scenes. What makes this particular story especially fascinating is not just that a sea disappeared, but that it came back. The Mediterranean today is not a fossilized memory of water. It is alive, active, full of motion and sound. Somewhere in its long history, after all that drying and salt building and reshaping, the connection to the Atlantic was restored. Water rushed back in, filling the basin once more, covering those bright salt plains and deep river valleys with a new layer of blue. But we're getting ahead of ourselves. For now, it is enough to sit with the idea of absence, a familiar shape on the map that, for a vast stretch of time, was not filled with water, but with air, heat, dust, and silence. A place where rivers plunged into a deep, dry basin instead of gently meeting the sea. A region where the line between land and water was constantly being redrawn. As you settle into this thought, you might notice how it changes the way you picture coastlines, seas, and even the ground beneath your feet. The solid, dependable earth suddenly feels a little more flexible, a little more willing to rearrange itself given enough time and the right conditions. It invites a kind of quiet curiosity, the sort that does not demand immediate answers, but is content to follow a story wherever it happens to lead. Let the image of that vanished Mediterranean rest gently in your mind. A sea that was not always a sea, a familiar place that once became something entirely different, and a reminder that even the largest features of our planet are, in their own way, temporary visitors in a much longer, deeper story that continues to unfold, quietly, beneath every wave and every step we take. Standing on a modern shoreline, it is easy to believe in permanence. The land feels solid under your feet. The water moves in a steady, predictable rhythm. Waves arrive, break, retreat, and return again, as though they have been practicing this small, dependable routine for millions of years without ever getting tired of it. Along the Mediterranean, this feeling is especially strong. The coastlines are lined with ancient cities, old harbours, and weathered stone walls that seem to whisper of long histories and human stories layered one on top of another. It feels like a place that has always been here, shaped long ago and then politely left alone. But if you linger with that thought for just a moment, it begins to soften. The coast, like everything else on this planet, is not a finished product. It is a work in progress, one that has been revised, erased, and redrawn more times than any map could ever capture. The familiar outline of the Mediterranean basin, the curves of southern Europe, the sweep of North Africa, the islands scattered like stepping stones across the water, all of these features are snapshots in a much longer sequence of changes that stretch far beyond human memory. To understand how a sea could disappear, it helps to first let go of the idea that coastlines are fixed boundaries. They are more like conversations between land and water, and those conversations can shift tone over time. Sometimes the water speaks more loudly, pushing inland and flooding low-lying areas. Sometimes the land answers back, rising up or extending outward, claiming ground that once lay beneath waves. If you could watch the Mediterranean region from very far above and very far back in time, you would see a slow, almost graceful dance between continents. Africa and Europe, which now face each other across the sea, have not always held this particular pose. They have drifted, rotated, nudged, and pressed against one another, guided by the deep, steady movement of Earth's tectonic plates. These plates are not fast. They move at about the speed your fingernails grow. But over millions of years, that quiet persistence adds up. Oceans open, seas close, mountains rise, basins form. The Mediterranean itself exists because of this long history of motion, because of ancient oceans that once filled the space between larger land masses, and because of collisions and separations that reshaped the region again and again. Long before the Messinian Salinity Crisis, there was another sea here, even larger and more open. Geologists call it the Tethys Ocean, a vast body of water that once separated the northern continents from the southern ones. As Africa slowly drifted northward, the Tethys began to shrink. Land bridges formed, islands rose, and what remained of that ancient ocean gradually took on the shape of the Mediterranean we recognise today. By the time we arrive at the period just before the sea began to vanish, the Mediterranean was already a kind of in-between place. It was not a fully open ocean like the Atlantic, but it was not an isolated lake either. It depended on narrow connections, especially in the region we now know as the Strait of Gibraltar, where water flowed in from the west, and on other smaller passages in the east that linked it to what would eventually become the Black Sea and beyond. Those connections were its lifelines. Through them came not only water, but also currents, nutrients, and living creatures. Fish, plankton, and countless other forms of marine life moved in and out, mixing populations and spreading across wide distances. The Mediterranean was part of a much larger system, breathing in and out through these geological doorways. Now, picture those doorways as landscapes rather than lines on a map. Instead of imagining a neat, clean strait of water between two cliffs, think of a broad, complex region where land and sea intermingled. Shallow shelves, low-lying plains, small islands and rising ridges would have made the area sensitive to even slight changes in sea level or land height. A few metres of uplift here, a small drop in water level there, and suddenly a wide channel becomes a narrow passage. A narrow passage becomes a trickle becomes nothing at all. What makes this especially interesting is that these changes do not need dramatic earthquakes or sudden, violent events to get started. They can begin with slow, steady pressure from colliding plates, or with the gradual build-up of sediments carried by rivers and deposited over thousands of years. Each grain of sand, each layer of mud adds a tiny bit of weight, a tiny change in shape, until the landscape quietly transforms. Along the edges of the Mediterranean basin, rivers have always played a role in this process. The Nile, the Rhone, the Po, and many others have been carrying material from deep inland and delivering it to the sea for millions of years. Over time, they build deltas, extend coastlines, and fill in shallow areas. If the sea level drops even slightly, these deltas can push farther out, turning former seabed into dry land. So when we talk about a familiar coastline that was not always there, we're not just speaking in a poetic sense. We're talking about real physical ground that has been underwater in one era and exposed to air in another. Entire plains, now used for farming or crossed by roads and cities, were once part of the seabed. In other periods, those same areas might have been flooded again, waves rolling over what would one day become dry land. During the lead-up to the Mediterranean's great drying, this process of change would have been unfolding quietly but steadily. Shorelines would have crept outward as water levels began to fall. Bays would have turned into lagoons, then into salt flats. Islands might have grown larger, connecting to the mainland through newly exposed land bridges. For animals and early human ancestors in the region, this could have opened new migration routes, new hunting grounds, and new challenges. Imagine a herd of animals following a familiar path along the coast, only to find that the shoreline has shifted, that the water now lies farther away than it did in the memory of older members of the group. Over generations, those changes would become part of the landscape of instinct and habit. What was once a beach becomes a grassy plain. What was once a shallow channel becomes a dry crossing. For the sea itself, these shifting boundaries meant a slow but growing sense of confinement. With less room to spread and fewer places to draw in fresh water from the open ocean, the Mediterranean began to behave less like a sea and more like a vast, shallow basin. Evaporation, always present, started to play a more dominant role. You can see a small-scale version of this today in places like the Dead Sea or the Great Salt Lake. These bodies of water have limited connections to larger systems and lose much of their water to evaporation. Over time, they become saltier and more concentrated. The Mediterranean during the Messinian period was beginning to move in that same direction, just on a far grander scale. As the water level dropped, the coastline would not have retreated in a smooth, even line. It would have followed the shape of the land, revealing ridges, valleys, and shelves in a complex pattern. Some areas might have remained wet, fed by rivers or underground springs, forming oases of life in an increasingly dry environment. Other areas would have become harsh, exposed plains of sediment and salt, difficult for plants and animals to cross. The climate around the basin may have responded to these changes as well. Large bodies of water tend to moderate temperatures, keeping nearby regions cooler in summer and warmer in winter. As the Mediterranean shrank, that moderating influence would have weakened. The surrounding lands might have experienced hotter summers and colder winters, creating a more extreme environment for the creatures living there. This feedback between land, water, and air is one of the quiet themes of Earth's history. A small change in one part of the system can ripple outward, influencing weather patterns, ecosystems, and even the movement of species across continents. The disappearing coastline of the Mediterranean was not just a local curiosity. It was part of a larger web of changes that touched regions far beyond the basin itself. One of the most striking consequences of a falling sea level is what happens to rivers. When the level of the water they flow into drops, rivers respond by cutting downward. They carve deeper channels into the land, creating steep valleys and canyons as they race to reach the new, lower base level. During the Messinian period, rivers flowing into the Mediterranean would have done exactly that. The Nile, for example, may have cut a deep canyon through what is now Egypt, reaching far below the modern sea level. Similar features have been identified in other river systems around the basin. These buried valleys, now filled in by later sediments, are like scars left behind by the great retreat of the sea. If you could walk through those landscapes at the time, you might find yourself standing at the edge of a vast drop where a river plunged into the depths of the basin below. Instead of a gentle, meandering flow into a calm sea, you would see water rushing down steep slopes, carrying sediment and energy into a world that was growing drier and more mineral-rich by the day. These dramatic features remind us that a coastline is not just a line where land meets water. It is a dynamic zone, shaped by forces coming from above, below, and far away. It responds to the slow push of tectonic plates, the steady work of rivers, the invisible lift of evaporation, and the shifting patterns of climate. For the people who live around the Mediterranean today, the coastline is a place of connection. It links cultures, trade routes, and histories. But in the deep past, it was also a frontier, a moving boundary between very different worlds. On one side, a shrinking, increasingly salty basin. On the other, vast stretches of land adapting to the loss of a neighbouring sea. There is something quietly humbling about realising that the ground beneath your feet might once have been underwater, and that the water you see today might one day retreat again. It does not make the present feel less real, but it does place it within a much longer story, one where change is the only truly constant element. As you let that idea settle, you might find your own surroundings taking on a slightly different feel. The walls of your room, the street outside, the familiar landmarks in your town or city, all of them sit on layers of history that extend far beyond human memory. Beneath them are sediments, rocks, and fossils that speak of oceans, rivers, forests, and deserts that came and went long before any written record. The Mediterranean's familiar coastline is just one chapter in that deep layered narrative. It is the version we happen to see now, shaped by a long sequence of events that includes not only the dramatic drying of the Messinian period, but also the equally dramatic return of the sea that followed. And that return, when it finally came, would transform the basin once more, drowning valleys, reshaping shores, and restoring the blue expanse that feels so natural to us today. But before that moment of renewal, there was a long stretch of waiting, of slow adjustment, of land and water learning to live with a very different set of boundaries. Long before anyone could have pointed to a narrow strait on a map and called it a gateway, water already understood the idea of boundaries. It moved according to the shape of the land, the pull of gravity, and the quiet push of winds and currents that travelled across its surface. It flowed where it could, paused where it must, and always, in its own patient way, tested the edges of the world around it. The story of the Mediterranean's great change is in many ways a story about those edges becoming firmer, more defined, and eventually almost closed. To picture this moment in Earth's long timeline, it helps to imagine the region not as a set of modern countries and coastlines, but as a wide, restless zone where continents lean toward one another, like old acquaintances who are slowly running out of space between them. Africa was drifting north. Europe, in its own steady motion, was shifting south and east. Between them lay the Mediterranean basin, a broad, low-lying region that held water because it had room to do so. The most important of its connections to the wider world lay to the west, in the area we now call the Strait of Gibraltar. Today, it is a familiar sight on satellite images and travel guides, a narrow but clearly defined channel between Spain and Morocco, where the Atlantic Ocean pours into the Mediterranean. But during the time we were exploring, this region was not a clean, sharp opening. It was a complex, changing landscape made up of shallow seas, low ridges, and rising land that responded to the slow pressure of moving plates beneath it. Think of it less as a door, and more as a hallway with a floor that can tilt and rise. When the floor is low, water flows freely through. When it lifts even a little, the passage becomes shallower, slower, more restricted. The difference between an open connection and a nearly closed one can be measured in meters, not kilometers, which is part of what makes this story so subtle and so powerful. As Africa continued its quiet push northward, parts of the seafloor in this region were compressed and lifted. Sediments that had once settled gently underwater were folded, stacked, and raised toward the surface. Over long stretches of time, what had been underwater hills became low islands. What had been shallow channels became narrow, winding passages. Water still flowed through, but it had to work a little harder to do so. At the same time, the climate of the region was playing its own role. The Mediterranean sits in a zone where warm, dry air often dominates, especially during certain seasons. Evaporation was already a strong force, pulling water from the sea and sending it back into the atmosphere. As long as the Atlantic connection remained wide and deep enough, this loss was balanced by an inflow of fresh seawater from the west. But as that connection narrowed, the balance became more delicate. You can picture it like a bowl with a small crack at the bottom. If you pour water in faster than it leaks out, the bowl stays full. If the leak widens or the pouring slows, the water level begins to drop. In the case of the Mediterranean, the pouring was the Atlantic inflow, and the leak was evaporation under a warm sun. Geological evidence suggests that the region did not close all at once. There were likely periods when the connection was strong, followed by times when it weakened, perhaps even shut briefly, only to reopen again. Each of these fluctuations would have left its mark on the basin. Salinity levels would rise and fall, water levels would creep down and then recover. Life in the sea would have been forced to adapt again and again to changing conditions. For the creatures living in the Mediterranean at the time, This would not have been a quiet background process. Changes in salinity, even small ones, can be stressful for marine life. Some species can tolerate a wide range of conditions, others are far more sensitive. As the water became saltier during periods of reduced inflow, certain organisms would have struggled, while others might have found new opportunities in the shifting balance. Plankton communities, which form the base of the marine food web, are especially responsive to changes in water chemistry. A shift in plankton populations can ripple upward, affecting fish, larger predators, and everything else that depends on them. Over time, the Mediterranean's ecosystem would have begun to look different, shaped by the repeated narrowing and widening of its western gate. But the western connection was not the only boundary that mattered. To the east, the Mediterranean was linked, in a more complex and indirect way, to other bodies of water through a series of basins and passages. These connections too were influenced by tectonic movement and sea level changes. The entire region was a patchwork of shallow seas and rising land, and the pattern was always in motion. What makes this especially fascinating is how small changes, repeated over long periods, can lead to a tipping point. For thousands of years, the system might remain in a kind of uneasy balance. Then, a slight uplift in the land or a subtle shift in climate could push it past a threshold. Once that happened, the process of drying could accelerate. As the Atlantic inflow weakened, the Mediterranean began to lose more water than it gained. The sea level started to fall, not dramatically at first, but steadily enough that the change would have been noticeable over generations. Shorelines moved outward, shallow areas became exposed, the remaining water became more concentrated with salt. This concentration had a feedback effect. Saltier water is denser, and density influences how water moves. Currents that once mixed the basin more thoroughly may have slowed or changed their patterns. Areas of stagnant water could have developed, further stressing marine life and altering the chemistry of the sea. Along the edges of the basin, rivers responded to the falling water level by cutting deeper into the land. Their channels became steeper and their flow more energetic. Sediments were carried farther down, adding to the layers of material building up in the deepest parts of the basin. Each grain of sand and silt that settled there became part of the geological record of this long drawn-out transition. If you were able to hover above the region during this time, watching it unfold in fast motion, you might see a slow tightening of the connection points, like fingers closing around a fragile thread of water. The Mediterranean would appear to shrink, not just in area, but in its relationship to the wider ocean. It would become more inward-looking, more self-contained, more dependent on the limited water sources within its own basin. The idea of gates in this story is a useful one, even if it simplifies a much more complex reality. There was no single door that slammed shut. Instead, there were zones of contact that became shallower, narrower, and less reliable over time. The flow of water through them became more sensitive to small changes in sea level, wind and pressure differences between the Atlantic and the Mediterranean. Modern measurements show that even today the Strait of Gibraltar is a dynamic place. Surface water from the Atlantic flows into the Mediterranean, while denser, saltier Mediterranean water flows back out beneath it, creating a layered exchange. This balance maintains the Mediterranean's salinity and water level. During the Messinian period, this exchange would have been far more fragile. A slight rise in land or drop in sea level could disrupt it entirely. One way to imagine this is to think of two connected pools at different heights, joined by a narrow channel. As long as the channel is deep enough, water can flow freely between them, equalizing their levels. If the channel becomes shallow, the flow slows. If it becomes too shallow, the higher pool can no longer supply the lower one, and the lower pool begins to drain through evaporation or other losses. In the case of the Mediterranean, the higher pool was the Atlantic, and the lower pool was the basin itself. As the channel between them became shallower, the Mediterranean's ability to maintain its water level weakened. What is remarkable is how much of this story we can reconstruct from the rocks. Layers of sediment deposited during this time show repeated patterns of salt and gypsum, indicating cycles of evaporation and partial refilling. These layers are like the rings of a tree, each one marking a period of change. By studying their thickness, composition and distribution, scientists can piece together a timeline of how the basin responded to the opening and closing of its boundaries. Some of these salt layers are incredibly thick, suggesting that enormous volumes of water evaporated, leaving behind their dissolved minerals. This is not something that could happen in a single brief event. It requires sustained periods of limited inflow and high evaporation, pointing to a long phase when the gates to the Atlantic were, if not completely closed, at least only barely open. As the Mediterranean continued to lose water, its surface dropped farther below global sea level. This would have increased the pressure difference between the basin and the Atlantic, potentially encouraging water to rush in during periods when the connection briefly deepened or reopened. The result may have been dramatic inflow events, followed by renewed drying when the passage narrowed again. These pulses of connection and isolation would have shaped the landscape in complex ways. Channels carved by inflowing water could have been exposed and modified during dry periods. River valleys might have been deepened, then partially flooded, then deepened again. The basin floor would have been layered with alternating deposits of sediment and evaporated minerals, building a record of each cycle. For the surrounding land, these changes meant that the Mediterranean was no longer a stable neighbour. Its presence or absence influenced local climates, wind patterns, and the availability of water. Areas that once benefited from the moderating effect of a large sea may have become drier and more extreme. Plants and animals adapted, migrated, or disappeared in response. There is a quiet drama in this process, one that unfolds without any single moment of obvious crisis. No towering wave announces the closing of the gates. No sudden collapse signals the beginning of the great drying. Instead, there is a slow, persistent tightening of connections, a gradual shift in balance, a steady accumulation of small changes that, together, lead to a very large outcome. It invites a different way of thinking about how Earth changes. We often imagine the planet as a place shaped by rare, catastrophic events, and those do happen, from massive volcanic eruptions to asteroid impacts. But much of the world we see today is the result of processes that operate quietly, almost invisibly, over vast stretches of time. The Messinian Salinity Crisis is one of those stories, a reminder that patience can be just as powerful as force. As the gates continued to narrow, the Mediterranean moved closer to a point of no return. Each period of reduced inflow left behind more salt, lowered the water level a little further, and made the basin more vulnerable to the next restriction. Over time, the system became increasingly sensitive, like a balance scale that tips more easily with each added weight. This is the moment in the story where the idea of boundaries becomes especially meaningful. The Mediterranean was not just bounded by land, it was bounded by its own past, by the layers of salt and sediment it had already accumulated, by the shape of the basin that had been carved long before, and by the climate that continued to pull water into the sky day after day. Water, in its endless motion, had found the limits of where it could go, and those limits were slowly closing in. You might notice how it echoes in smaller, more familiar ways. Lakes that shrink during droughts. Rivers that change course as sediment builds up. Coastlines that retreat or advance with rising and falling sea levels. The same principles apply, just on a different scale. The Earth is always negotiating its boundaries, always testing how far water can flow and where it must stop. In the case of the Mediterranean, that negotiation was reaching a critical phase. The basin was becoming more isolated, more concentrated, more inward. The stage was being set for a transformation that would turn a vast sea into something very different. There was no single sunrise that marked the moment the Mediterranean began to disappear. No dramatic crack in the sky, no thunderous sound that echoed across 3 continents. Instead, The change announced itself in much quieter ways, the kind you might miss if you were not paying close attention. A shoreline that seemed a little farther away than it used to be, a bay that no longer filled quite as deeply as it had in the memory of the last generation, a river that suddenly found itself flowing faster, steeper, cutting into its own path as if in a hurry to reach something that had moved out of reach. This is how the shrinking began, not as a single day, but as a long, unfolding moment stretched across centuries. Imagine standing somewhere along the ancient Mediterranean coast, perhaps on a rocky rise that overlooks a wide curve of water. You might see fishing boats, if there were people there, or flocks of birds skimming the surface in search of food. The scene would feel stable, familiar, the kind of place that invites the assumption that tomorrow will look much like today. But beneath that calm surface, the balance that kept this sea full was tipping. Water was still flowing in from the Atlantic, but less of it. The narrow western passages had become shallower, more sensitive to changes in land and sea level. At the same time, the sun continued its steady work, lifting water into the air through evaporation. Day after day, season after season, more water left the basin than entered it. At first, the difference would have been almost impossible to notice. A few centimetres here, a metre there. Over a human lifetime, it might not have seemed like much at all. But over thousands of years, those small changes added up. The Mediterranean began to draw back from its own edges. The first places to feel this retreat were the shallow regions. Coastal shelves, sandbanks, and low-lying bays would have emerged from the water, turning into stretches of damp ground that glistened in the sun. Tidal pools, once refreshed by regular waves, became isolated pockets. Some dried out completely, others grew saltier as water evaporated and left its minerals behind. Life in these areas faced a choice: move, adapt, or vanish. Plants that could tolerate salty soil might have crept into newly exposed ground. Birds and animals may have explored these fresh landscapes, finding new feeding grounds where there had once been only water. For marine creatures trapped in shrinking pools, conditions grew harsher. As salinity increased, oxygen levels could drop, making survival more difficult. Farther out in the basin, the deeper waters were slower to respond, but they too were changing. As the overall water level fell, currents shifted. The patterns of circulation that once mixed the sea from top to bottom began to weaken. Some areas may have become stagnant, warm and heavy with salt. One of the most striking consequences of a falling sea is what happens at the mouths of rivers. Rivers do not like to flow uphill. They follow gravity, always seeking the lowest point they can reach. When the level of the water they flow into drops, they respond by cutting downward, carving into their own beds to reach that new, lower target. During this long period of shrinkage, rivers around the Mediterranean began to do exactly that. The Nile, carrying water from deep in Africa, may have carved a deep canyon through what is now a broad, flat plain. The Rhone, the Po, and many others would have cut steep valleys, creating dramatic landscapes that would later be buried under layers of sediment when the sea returned. If you could have walked along one of these riverbanks at the time, you might have found yourself standing at the edge of a sudden drop, looking down into a steep, winding channel where water rushed toward the deepening basin below. The sound of that flow would have been different from the gentle lapping of waves against a shore. It would have been faster, sharper, carrying with it the energy of a river that had found a long, steep path to follow. The basin itself, now lower than the surrounding lands by hundreds of meters in some places, would have begun to take on a very different character. Instead of a broad, open expanse of water, it became a vast, sun-baked depression, filled in some areas with shallow hypersaline pools and in others with dry, mineral-covered plains. Salt, once dissolved invisibly in the water, started to make its presence known. As water evaporated, minerals crystallized out of solution. Layers of salt and gypsum settled on the basin floor, building up gradually, quietly, like snowfall in a place where winter never truly ends. These deposits did not form in a single, uniform sheet. They accumulated in patterns, influenced by the shape of the basin, the remaining water flows, and the cycles of partial refilling and renewed drying. Some areas saw thick, massive layers of salt. Others recorded thinner bands, marking shorter periods of evaporation. Over time, these layers would become a kind of geological diary, preserving the story of the shrinking sea in stone. Above the basin, the air may have taken on a different quality. With less water below to moderate temperatures, the region could have grown hotter and drier. Winds might have picked up fine grains of salt and dust, carrying them across the surrounding lands. These particles could settle on leaves, soil and rock, subtly altering the chemistry of the environment. Rain, when it came, would wash some of that salt back toward the lowest points, feeding the growing mineral fields below. It is a quiet cycle, but a persistent one, reinforcing the transformation of the basin into a place defined as much by what it had lost as by what remained. For the creatures living in and around the Mediterranean, this was a time of transition. Some marine species likely retreated toward the remaining deeper waters or out through the western passages when they could. Others, trapped in increasingly harsh conditions, would have disappeared from the basin entirely. On land, new opportunities may have opened. The newly exposed plains and valleys could have become migration routes for animals, connecting regions that were once separated by water. Early human ancestors, if they were in the area at the time, might have found these land bridges useful, though the climate and conditions would not have made for an easy journey. It is worth pausing here to consider the scale of what was happening. The Mediterranean is not a small sea. It covers an area of roughly 2.5 million square kilometres today. To shrink something of that size, even gradually, requires an enormous shift in the balance of water moving in and out. This is why the narrowing of the Atlantic connection mattered so much. As long as the inflow could keep up with evaporation, the sea could maintain itself. Once it could not, the process of drying became self-reinforcing. Lower water levels meant more surface area exposed to sun and wind, which could increase evaporation. More evaporation meant higher salinity, which could alter currents and further limit mixing and replenishment. The basin, in a sense, became its own feedback system, drifting farther and farther from the conditions that had once defined it. What we know about this period comes not only from the salt layers beneath the sea, but also from clues preserved on land. Fossilized river channels, ancient shorelines, and sediment deposits all point to a time when the Mediterranean stood far lower than it does today. In some places, scientists have identified features that suggest the sea level may have dropped by more than a kilometre in certain parts of the basin. That is a staggering thought. Imagine standing at the edge of a cliff that looks down into what was once the heart of a sea, now transformed into a deep, dry valley. The scale of that drop would be hard to wrap your mind around, even if you could see it with your own eyes. And yet, for all its drama, this transformation unfolded slowly enough that no single moment could be labelled as the beginning. There was no line you could draw and say, on this day the Mediterranean started to shrink. Instead, there was a long, gradual transition, marked by countless small changes that, together, reshaped an entire region. This kind of change can feel strangely familiar when you think about it in human terms. Habits shift. Cities grow or decline. Climates warm or cool. Often, it is only when you look back over many years that you realise how much has changed. The Mediterranean's retreat followed a similar pattern, just on a much larger and slower scale. There is also something quietly compelling about the idea of a sea pulling back from the land, revealing hidden landscapes that had been submerged for millions of years. Rock formations, valleys and plains that had never known sunlight suddenly found themselves under an open sky. The ground, once shaped by the gentle pressure of water, was now shaped by wind, heat, and the rare but powerful touch of rain. In these newly exposed areas, erosion would have taken on a different character. Without the constant presence of water to smooth and soften surfaces, rock could crack under temperature changes. Salt crystals could grow in tiny fractures, prying stone apart grain by grain. Over time, this process could create strange sculpted landscapes, marked by sharp edges and mineral crusts. The basin floor, layered with salt and sediment, would have been a place of extremes. During rare wet periods, shallow lakes might have formed, reflecting the sky for a brief time before evaporating again. During long dry stretches, the ground would have been blindingly bright in the sun, a patchwork of white and pale hues stretching to the horizon. It is difficult to imagine what it would have felt like to stand in such a place. The air might have been dry, the heat intense, the silence broken only by the wind. In the distance, the steep walls of the basin would rise like a natural amphitheatre, reminding you that this vast, empty space had once been filled with water. And somewhere beyond those walls, the Atlantic Ocean still existed, still rolling and breathing in its own endless rhythm, separated now by a boundary that had become too narrow, too shallow, too fragile to keep the Mediterranean alive in the way it once had. The idea that two bodies of water, so close in a global sense, could live such different lives at the same time is one of the more intriguing aspects of this story. While the Mediterranean dried and salted, the Atlantic continued its vast open circulation, connecting distant shores and moderating climates across half the planet. This contrast highlights just how much geography matters. A few tens of kilometres of land, a slight uplift in the crust, a narrow passage that becomes just a little too shallow, and the fate of an entire sea can change. As the Mediterranean continued to shrink, it moved farther away from the conditions that would allow it to easily recover. The salt layers grew thicker. The basin floor sank under the weight of accumulated minerals. The surrounding rivers carved deeper paths, making the landscape more dramatic and more complex. Each of these changes made the eventual return of the sea, when it would come, a more powerful and transformative event. The deeper the basin, the greater the potential energy of the water that would one day rush back in. The thicker the salt layers, the more influence they would have on the shape and behaviour of the seafloor in the future. But for now, in this long, quiet phase of retreat, the Mediterranean was learning what it meant to be something other than a sea. There is a certain stillness in that idea, a sense of waiting without any clear sense of what comes next. The basin, carved and reshaped by water for millions of years, now found itself defined by its absence. The land around it adjusted, life adapted, and the planet continued its slow, patient movements beneath it all. Lakes, rivers, even oceans can feel permanent when you see them every day or on every map. But in the longer view of Earth's history, they are as temporary as mountain ranges and ice sheets, appearing and disappearing as the conditions that support them shift. The day the Mediterranean started to shrink was not a moment you could circle on a calendar. It was a long, drawn-out transition, one that unfolded so slowly it could only be recognised in hindsight. And yet, it set in motion a chain of events that would lead to one of the most dramatic transformations in the planet's recent geological past. At first, the salt did not announce itself in any dramatic way. There were no great white fields stretching to the horizon, no blinding plains that demanded attention. It began quietly, almost politely, as a subtle change in the water itself. The sea grew heavier, denser. The taste of it, if you could have dipped a hand and brought a drop to your lips, would have been sharper than before. Not by much at first, just enough to hint that something in the balance had shifted. Salt, after all, is always there in seawater. It drifts invisibly between molecules, carried by currents, mixed by waves, unnoticed by most forms of life that have learned to live with it. But when water leaves and salt stays behind, the relationship changes. What was once a background presence begins to move toward the foreground. As the Mediterranean continued to lose more water than it gained, the concentration of dissolved minerals rose. The basin became, in effect, a giant natural evaporating dish. Day after day, sunlight warmed the surface. Wind carried away moisture. Rivers still delivered fresh water and new minerals from the surrounding lands, but the overall direction of the system was clear. More was leaving than arriving. At a certain point, the water could no longer hold all the salt it carried. There is a limit to how much can stay dissolved. When that limit is reached, the excess begins to settle out, forming tiny crystals that sink slowly toward the bottom. This is where the image of salt falling like snow becomes useful, not because the process was sudden or dramatic, but because of the quiet persistence of it. Grain by grain, crystal by crystal, minerals drifted downward through the remaining water, settling onto the basin floor. There was no sound, no visible flurry, just a slow, steady accumulation that built up over years, centuries and millennia. If you could have hovered above the basin during this time, looking down through the thinning water, you might have seen a pale haze near the bottom. That haze would not have been clouds or mist, but countless tiny crystals catching the light as they descended. The deeper parts of the basin would have become brighter, more reflective, as layer upon layer of salt and gypsum spread across the floor. The process did not happen all at once or in the same way everywhere. Different minerals precipitate out of seawater at different concentrations. Calcium carbonate might settle first, followed by gypsum, and then halite, the familiar salt we sprinkle on food. Each phase marked a new stage in the drying of the basin, a new chapter in the chemical story unfolding beneath the shrinking sea. In some areas, shallow pools would have formed, isolated from the rest of the water. These pools would have evaporated more quickly, leaving behind thick crusts of minerals. In other places, deeper water might have lingered longer, allowing for thinner, more evenly spread layers. The result was a patchwork of deposits, thick in some regions, thinner in others, shaped by the contours of the basin and the patterns of remaining water flow. Over time, these layers grew to astonishing thicknesses. In some parts of the Mediterranean basin, salt deposits from this period reach hundreds of meters, even more than a kilometre in total thickness. It is difficult to picture that much material settling out of water, but when you remember the size of the sea that once filled this space, the scale begins to make more sense. The Mediterranean was not just losing water, it was turning itself inside out, transforming dissolved minerals into solid ground. The basin floor, once shaped by currents and sediment carried from distant lands, became a growing platform of crystalline layers. These layers were not smooth like a polished surface. They formed ridges, cracks, and patterns as they dried, expanded and shifted. Salt, in particular, has a way of moving even after it has solidified. Under pressure, it can flow slowly, like a very thick liquid, forming domes and folds in the layers above it. So even as the salt settled, it was already beginning to reshape the future seafloor in subtle ways. Above this growing mineral landscape, the air would have felt different from what we associate with a coastal environment. With less open water to moderate temperature and add moisture to the atmosphere, the region likely became drier and hotter. Winds sweeping across the basin could pick up fine salt dust from exposed surfaces and carry it outward, sprinkling the surrounding lands with a faint invisible coating. This salt dust may have affected soils, making it harder for some plants to grow while favouring others that could tolerate or even thrive in more saline conditions. The ecosystem around the basin would have slowly adjusted step by step to a world where the sea was no longer the dominant presence. For the animals that lived near the shrinking shoreline, the changing chemistry of the water would have been impossible to ignore. Fish and invertebrates adapted to normal marine salinity found themselves in an increasingly hostile environment. Some species likely retreated toward the last remaining connections to the Atlantic, following the flow of water out of the basin when they could. Others may have sought refuge in deeper pockets or in areas fed by rivers, where the water remained slightly fresher. Many would not have survived the transition. On land, the newly exposed basin floor created vast open spaces that had never existed in that form before. These plains of salt and sediment would have been harsh places, offering little shelter or food. During rare wet periods, thin sheets of water might have spread across the surface, dissolving some of the salt and then evaporating again, leaving behind new patterns of crystals. If you could have walked across one of these salt plains, the ground might have crunched underfoot, breaking into geometric patterns where the crust had dried and cracked. The light would have been intense, reflected back from the pale surface, making the horizon shimmer in the heat. The air might have carried a faint, sharp scent, a reminder of the minerals that now dominated this landscape. Rivers still flowing down from the surrounding highlands would have delivered fresh water and sediment into this basin of salt. Where they reached the floor, they could create temporary deltas, spreading mud and silt over the mineral layers. For a time, these areas might have supported small patches of life, plants and animals drawn to the presence of water in an otherwise dry and unforgiving environment. But even these oases were temporary. The relentless process of evaporation would eventually reclaim the water, leaving behind new layers of minerals on top of the riverborne sediments. The basin became a place of constant layering, a slow alternation between wet and dry, between flow and stillness. This pattern is recorded in the rocks today. When scientists drill into the seafloor beneath the modern Mediterranean, they find these alternating layers stacked like pages in a book. Each one tells of a time when water covered the basin, followed by a time when it retreated and left its dissolved contents behind. What makes this record especially valuable is that it allows us to see not just that the sea dried, but how it did so. The thickness and composition of each layer reveal the intensity and duration of each drying phase. Some periods appear to have been especially severe, marked by thick deposits of salt that suggest long stretches of near-complete isolation from the Atlantic. Other layers are thinner, hinting at times when water flowed back in more freely, even if only briefly. The idea of salt falling like snow also carries a sense of quiet inevitability. Snow does not rush. It accumulates. It transforms a landscape not through force, but through persistence. In the same way, the salt in the Mediterranean basin did not reshape the region in a sudden, violent event. It did so through a slow, steady process that, over time, produced one of the most dramatic geological features of the recent past. There is something almost meditative about thinking of this accumulation. Millions upon millions of tiny crystals, each one settling into place, building a structure that would outlast countless generations of living things. It is a reminder of how small actions, repeated endlessly, can lead to enormous outcomes. As the basin continued to dry and fill with minerals, its surface dropped farther below the level of the surrounding oceans. This increased the potential energy stored in the system. The deeper the basin became, the greater the difference in height between it and the Atlantic. This difference mattered, even if it did not show itself right away. It was like a reservoir being carved into the earth, waiting to be filled. The walls grew higher, the bottom sank lower. The potential for a dramatic return of water was quietly building, even as the basin itself seemed to be moving farther and farther away from anything resembling a sea. Salt in this context was not just a byproduct of drying. It became an active participant in shaping the future. Thick salt layers can influence how the Earth's crust behaves. Because salt is relatively soft and can flow under pressure, it can create zones of weakness where rocks above it shift, fold, or fracture. Over long periods, this can affect the formation of mountains, the movement of faults, and the shape of the seafloor. Even today, the buried salt layers beneath the Mediterranean influence the way oil and gas are trapped in underground reservoirs, guiding the movement of fluids through the rock. So the quiet snowfall of minerals during the Messinian period did not just create a record of the past. It laid the groundwork for changes that would continue to play out millions of years into the future. For the atmosphere above the basin, The growing salt plains would have altered how heat and moisture moved through the region. Pale, reflective surfaces can bounce sunlight back into the sky, potentially cooling the air just above the ground while contributing to rising temperatures higher up. The lack of open water reduced the amount of moisture available to form clouds and rain. These shifts could have influenced weather patterns not only around the Mediterranean, but in neighbouring regions as well. Climate is a system of connections, and changes in one area can ripple outward in ways that are difficult to trace. For the surrounding lands, the basin became a source of dust as well as salt. Winds sweeping across the exposed floor could lift fine particles into the air, carrying them across mountains and valleys. This dust could settle far from its source, adding minerals to soils in distant places, subtly altering their fertility and chemistry. In this way, the drying Mediterranean reached beyond its own boundaries, touching landscapes far from its former shores. It is also worth considering how this transformation might have looked from a distance. If you stood on a high ridge along the edge of the basin, you would not have seen a glittering expanse of blue. Instead, you might have looked out over a vast pale depression, stretching farther than the eye could see. In some places, thin sheets of water might have reflected the sky, but much of the view would have been dominated by mineral flats, winding river channels, and the distant haze of heat and dust. The sense of scale would have been overwhelming. This was not a dry lake or a small desert. It was a sea-sized absence, a place where something enormous had once been and was now, for a long stretch of time, not. And yet, even in this phase of apparent emptiness, the basin was not static. Rivers continued to flow. Minerals continued to settle. Tectonic forces continued their slow work beneath the surface. The earth did not pause just because the water had gone. This is one of the quieter lessons of the Messinian Salinity Crisis. Absence is not inactivity. A dry basin is still a place of change, of movement, of ongoing processes that shape what will come next. As the salt layers grew thicker, the basin floor sank further under their weight. The difference in elevation between the Mediterranean basin and the Atlantic increased. The narrow western gateways, already fragile, became even more critical. A small change in their height or depth now carried much greater consequences. At some point, the balance would tip in the opposite direction. The potential energy stored in the height difference between ocean and basin would find a release. Water would return, not gently, but with a force that matched the long, patient build-up of the dry period. But that moment still lies ahead in our slow walk through this story. For now, we remain in this phase of quiet accumulation. The salt continues to fall, crystal by crystal. The basin continues to deepen, layer by layer. The surrounding lands adjust to a neighbour that has become a vast reflective plain instead of a breathing sea. If you let this image settle in your thoughts, you might notice how it reframes the idea of change, not as something that always arrives with noise and spectacle, but often as something that happens in small, steady increments, almost too subtle to notice until the transformation is complete. The Mediterranean snowfall of salt is a reminder of that quieter kind of power, a power that works through patience, repetition, and the simple fact that, given enough time, even the largest systems can be reshaped by the smallest of actions. From a distance, a river looks like one of the most straightforward things in the world. It begins somewhere high, perhaps in mountains or rolling hills, and it makes its way downhill following gravity's quiet instructions until it reaches a lake, a sea, or an ocean. We grow up with that idea so firmly in place that it feels almost like a rule of nature that cannot be broken. Water goes down. Rivers flow towards something lower. End of story. But during the long, strange transformation of the Mediterranean basin, that simple rule began to feel a little less certain. The rivers that once wandered gently into a wide, open sea found themselves facing a new kind of landscape. The water they were meant to meet had moved away, dropping lower and lower, turning a familiar destination into a deep, distant target. gravity was still in charge, but the path it pointed to had grown steeper, longer, and far more dramatic than before. Imagine a river that has spent thousands of years flowing into a calm, shallow shoreline. Its channel is broad, its pace is relaxed. Sediment settles gently along its banks, building up soft curves and wide deltas. Fish move easily between fresh and salt water. Birds gather in the wetlands that form where land and sea meet. It is a place of gradual transitions. Now imagine that the sea suddenly lies hundreds of meters lower. The river does not stop flowing. It cannot. It still receives rain, snowmelt and groundwater from far upstream. The water still needs somewhere to go, but instead of meeting the sea after a long, shallow journey, it now stands at the edge of a vast drop. This is where the idea of rivers learning to climb comes in. Not because they truly flow uphill, but because they begin to cut their way down through the land with such determination that it can feel, from a certain point of view, like they are working against the shape of the world rather than simply following it. As the Mediterranean basin dried and sank, rivers all around its rim began to respond. Their base level, the lowest point they could flow toward, had fallen. To reach it, they needed to carve deeper channels. The result was a process known as down-cutting, where a river erodes its bed instead of just meandering across a floodplain. Over long stretches of time, this down-cutting can create deep, narrow valleys and canyons. The gentle slopes of a river's course become steeper. Water speeds up. The energy of the flow increases, and with it the river's ability to carry away rock and sediment. Picture standing beside one of these rivers during that period. Instead of a wide, slow-moving stream bordered by reeds and soft banks, you might find yourself looking down into a sharply defined channel. The water would rush past faster and louder, its surface broken by rocks and uneven ground. The banks would be steeper, perhaps even cliff-like in places, revealing layers of soil and stone that had once been buried. This transformation did not happen overnight. It unfolded over thousands of years, with the river cutting a little deeper with each season of heavy rain or melting snow. Floods, which in a stable system might spread out across a plain and deposit fertile sediment, now became powerful tools of erosion. They surged through the narrowing channels, scouring away rock and soil, pushing the riverbed ever lower. The Nile is one of the most famous examples of this process during the Messinian period. Today, it flows across a broad, flat delta before meeting the Mediterranean. But geological evidence suggests that when the sea level dropped, the Nile carved a deep canyon through what is now northern Egypt. In some places, this ancient channel may have reached more than a kilometre below the modern sea level. It is difficult to visualise that kind of depth when you stand on the Nile's banks today, watching the river move lazily past fields and cities. But beneath those familiar landscapes lie layers of sediment that fill in a much older, much deeper path. A hidden record of a time when the river raced toward a far-away, sun-baked basin instead of a nearby sea. The same story played out around the entire rim of the Mediterranean. The Rhône, flowing from the Alps through what is now southern France, likely carved a deep valley as it chased the retreating sea. The Po, draining the northern Italian plains, and many smaller rivers all responded in similar ways, each cutting its own dramatic route toward the basin below. These valleys did not exist in isolation. They reshaped the surrounding landscape, creating steep walls, exposed rock faces, and new patterns of drainage. Rain falling on the land now had different paths to follow. Streams that once spread out across wide plains were captured by these deepening channels, feeding into the growing network of down-cutting rivers. In this way, the drying of the Mediterranean basin reached far beyond its immediate shores. It influenced the shape of the land hundreds of kilometres inland, altering how water moved across entire regions. There is a certain quiet intensity in imagining this process. A river, which we often think of as a gentle, life-giving presence, becomes a powerful sculptor of the land. It is still guided by the same simple principle, follow the lowest point, but the expression of that principle becomes far more dramatic when the destination lies deep below. If you were able to look down into one of these canyons during the height of the basin's dryness, you might see a ribbon of water far below glinting in the light. The air near the top of the valley could be dry and hot, while the bottom might hold cooler, more humid conditions, shaded by the steep walls on either side. These microclimates could create pockets of life in an otherwise harsh landscape. Plants might cling to ledges where moisture collected. Animals could use the valleys as sheltered routes for movement. In a world dominated by salt flats and dry plains, these river corridors would have been among the few places where fresh water was a reliable presence. For early human ancestors, if they were in the region at the time, such corridors would have been especially important. Water sources shape movement, settlement, and survival. A deep river valley cutting toward the heart of the basin might have served as a natural pathway, guiding migration and offering resources in an otherwise challenging environment. The idea of rivers climbing also reflects how they began to interact with the changing topography in unexpected ways. As the basin floor sank and salt layers built up, the surrounding land was not static. Tectonic forces continued to lift some areas and lower others. This meant that a river's path could be influenced not just by erosion, but by the slow movement of the ground itself. In some cases, land uplift upstream might have increased the river's gradient, making its flow even more energetic. In other areas, subsidence could create new low points, redirecting streams and altering drainage patterns. The landscape became a dynamic puzzle, with water constantly adjusting to a shifting set of instructions from the earth beneath it. Over time, these changes left behind a complex network of buried valleys and channels. When the Mediterranean eventually refilled, many of these features were flooded and then gradually filled in with sediment. Today, they lie hidden beneath plains, deltas, and coastal regions, detectable only through drilling, seismic imaging, and careful geological mapping. These hidden landscapes are like ghosts of a different world, reminders that what we see on the surface is often just the latest layer in a much deeper story. There is something almost poetic, even without trying to be, in the way these rivers responded to the loss of the sea. They did not dry up and disappear. They did not stop and wait. They adapted. They changed their behaviour, their shape, their relationship with the land. They followed gravity into a new kind of journey, one that required more effort, more energy, and more time. This adaptability is a recurring theme in Earth's history. Systems rarely shut down entirely when conditions change. Instead, they shift into new modes of operation. The rivers of the Mediterranean basin became agents of connection in a landscape that was increasingly defined by isolation. As the basin floor grew deeper and more mineral-rich, the rivers continued to deliver fresh water and sediment. This created a contrast between the harsh, salty environment of the basin and the relatively fresher, more fertile corridors along the river paths. In some areas, this contrast may have been stark, like green threads running through a pale, dry expanse. The sediment carried by the rivers also played a role in shaping the basin itself. As water poured into the low-lying areas, it spread out, slowed down, and dropped its load of sand, silt, and clay. These deposits layered over the salt flats, creating alternating bands of mineral and sediment. Each layer recorded a moment when the river reached the basin and left a mark. Over thousands of years, these layers built up, adding weight to the basin floor and contributing to its gradual sinking. This in turn made the difference in height between the basin and the Atlantic even greater, setting the stage for the dramatic return of water that would come later. In this sense, the rivers were not just responding to the shrinking sea, they were actively shaping what would happen next. It is also worth thinking about how these deep valleys might have looked and felt to experience. Standing at the rim of one, you would see a long, winding cut in the land stretching toward the horizon. The walls might be marked with bands of colour, each representing a different layer of rock or soil, each telling of a different period in the region's past. The sound of water would echo up from below, carried on air currents that move through the canyon. During heavy rains or seasonal floods, that sound would grow louder, more urgent, as the river surged through its confined path. These were not gentle pastoral rivers anymore. They were powerful, focused, shaped by the need to reach a destination that lay far beneath the level of the surrounding world. For the surrounding ecosystems, this created a pattern of contrasts. Uplands and plains around the basin could be dry, dusty, and exposed. The valleys, by comparison, might have been ribbons of life, supporting plants and animals that could not survive elsewhere. This pattern of life clustering around water in an otherwise harsh environment is something we still see today in deserts and arid regions. The Messinian Mediterranean basin would have been a vast example of that principle, with rivers acting as lifelines across an enormous, challenging landscape. The phrase "learn to climb" also hints at how these rivers began to work their way back into the surrounding land, capturing smaller streams and extending their influence. As a river cuts deeper, it can erode its headwaters, the region near its source, pulling the boundary of its drainage basin farther upstream. This process, known as headward erosion, allows a river to steal water from neighbouring basins. In the Mediterranean region during this time, this could have led to changes in which areas drained toward the basin and which drained elsewhere. Watersheds, the invisible lines that separate one river system from another, may have shifted. A stream that once flowed toward a different sea or basin might have been redirected toward the deepening Mediterranean depression. These changes would have further integrated the surrounding landscape into the story of the shrinking sea, tying distant hills and valleys into a single interconnected system of flow and erosion. What emerges from all of this is a picture of a region in motion, even in the absence of waves and tides. Water still moved, still shaped, still connected. It simply did so in a different way. The rivers became storytellers of the basin's transformation, carving lines into the land that spoke of a missing sea and a new, lower world waiting below. Their valleys became records of a time when the destination of all this flowing water lay far deeper than anyone standing on the surrounding plains might expect. You might find yourself thinking differently about the rivers you know. The quiet stream in a park, the wide river crossing a city, the winding channel through farmland. Each one is following gravity, responding to the shape of the land and the level of the water it flows into. In the Mediterranean's past, that shape and that level changed dramatically, and the rivers responded in kind. They did not resist the new reality. They carved their way into it step by step, season by season, leaving behind a network of deep paths that would one day be hidden beneath new layers of water and sediment. Those hidden paths still exist. They lie beneath modern deltas, beneath coastal plains, beneath cities and fields. They are silent, buried witnesses to a time when the Mediterranean was not a sea, but a vast sunlit basin, and when rivers, in their own steady, determined way, learned how to reach a destination that lay far below the world they once knew. Down in the depths of the Mediterranean basin, far below the level where waves once rolled and boats once drifted, the world settled into a very different rhythm. This was no longer a place defined by tides, currents, and the gentle breathing of the sea. It became a low-lying landscape under an open sky, shaped by heat, dryness, and the slow, steady presence of salt. And yet, even here, even in a place that might seem empty at first glance, life did not simply step aside. It adjusted, it lingered, and in some corners it found ways to persist. Picture the basin at this stage not as a single uniform plain, but as a vast, varied world spread out over thousands of kilometres. There were deep depressions where the last remaining pools of water gathered, shallow flats where salt crusts formed pale, reflective surfaces, and winding channels carved by rivers that still carried fresh water down from distant mountains and highlands. The air above shimmered in the heat, the horizon often blurred, as if the land itself was breathing. In this environment, the difference between survival and disappearance could be measured in very small details. A patch of shade cast by a cliff, a trickle of fresh water seeping from the ground, a brief period of rainfall that left behind shallow puddles before the sun reclaimed them. Life, in all its quiet determination, learned to pay attention to these moments. Along the river corridors, the contrast between the harsh basin floor and the relative softness of flowing water would have been striking. Where rivers cut their deep paths toward the low point of the basin, their banks could support plants that needed more moisture than the surrounding plains could offer. These green ribbons may have been narrow, but they were lifelines. Grasses, shrubs, and perhaps small trees could take root in the sediment deposited by floods. Their roots would hold the soil in place, slowing erosion and creating small pockets of stability. Insects would gather around these plants, drawn by nectar, leaves, and the simple fact that this was one of the few places where water was reliable. Where insects gather, other creatures follow. Small animals might have used these river corridors as routes for movement and foraging, travelling along the paths carved by water in a landscape that otherwise offered little shelter. Birds could nest in the cliffs and ledges of the deep valleys, taking advantage of the updrafts created by warm air rising from the basin floor. In the shallow pools that formed in low-lying areas, life took on a different character. These pools were often temporary, appearing after rainfall or during brief periods when water flowed in from the remaining connections to the sea. Their salinity could change rapidly, becoming fresher when new water arrived and saltier as evaporation took over. Only certain kinds of organisms can tolerate that kind of instability. Microbes, algae, and small invertebrates are often among the first to move into such environments. Some thrive in salty conditions that would be deadly to most other forms of life. They form thin, colourful films on the surface of water or crusts on damp ground. Their presence subtle but persistent. These microscopic communities play an important role in shaping their surroundings. They can influence how minerals settle, how sediments bind together, and even how the ground absorbs or reflects heat. Over time, their activity can leave behind chemical signatures in the layers of rock and salt, quiet traces that scientists can read millions of years later. For larger animals, the basin was a place to pass through, rather than to settle in permanently. Herds moving between more hospitable regions might have crossed the dry plains, following the deep river valleys as guides. Predators could shadow these routes, relying on the same corridors to find water and prey. The climate at the bottom of the basin would have added another layer of challenge. With the sea gone, the moderating influence of a large body of water was absent. Days could become intensely hot, with sunlight reflecting off salt flats and pale sediments, amplifying the heat. Nights, by contrast, might cool quickly, as dry air and open skies allowed warmth to escape. These swings in temperature would test the limits of many organisms. Those that survived likely did so by finding shelter during the hottest parts of the day, burrowing into the ground, hiding in the shade of rocks or vegetation, or becoming active during cooler hours. There is something quietly remarkable about the idea of life persisting in such a place. It challenges the notion that environments must be gentle or stable to support living systems. Instead, it shows that life often finds a foothold in the margins, in the brief windows of opportunity between extremes. The remaining bodies of water in the basin, where the shallow lakes or deeper pools fed by rivers, would have been especially important. These were not just sources of drinking water. They were centres of activity, places where different forms of life intersected. In and around these pools, you might have found dense clusters of plants and animals, drawn together by the simple fact that water was present. The edges of these pools could support reeds or other moisture-loving plants. Insects would hover above the surface. Birds might gather to drink and feed. The ground nearby could be marked by the tracks of animals that visited regularly. These oases, however, were fragile. A long dry period could shrink them or cause them to disappear entirely. A sudden influx of salt-rich water could change their chemistry, making them uninhabitable for some species. Life in these areas was always negotiating with uncertainty. There is also the question of what remained in the deeper parts of the basin, where some water may have lingered for longer periods. These deeper pockets could have supported marine life that was able to tolerate high salinity and low oxygen levels. Certain species of fish and invertebrates are known today for their ability to survive in extreme conditions, such as hypersaline lakes and enclosed seas. In these isolated waters, populations could become cut off from the rest of their species, evolving along their own paths over time. This kind of isolation can lead to unique adaptations as organisms adjust to the specific challenges of their environment. But isolation also brings vulnerability. A change in conditions, a drop in oxygen, a spike in salinity, or the loss of a connection to fresh water could wipe out entire populations. The basin at this stage was a place of both persistence and fragility, where life could continue but rarely without risk. On land around the basin, the changes in environment would have influenced larger patterns of movement and survival. The drying of the Mediterranean may have altered regional climates, making some areas drier and others more seasonal. Plants adapted to wetter conditions might have retreated toward higher ground, or regions still influenced by large bodies of water. Animals, in turn, would have followed these shifts in vegetation. Migration routes could have changed, favouring paths along rivers and through valleys rather than across open, dry plains. Over long periods, these changes could influence the distribution of species across continents, shaping the patterns we see in the fossil record. For early human ancestors, if they were present in or near the region at the time, this would have been a challenging landscape. Access to water would have been a constant concern. The deep river valleys might have offered resources and routes, but the basin floor itself would have been difficult to inhabit for long periods. At the same time, the exposure of land bridges where sea once flowed could have opened new pathways between regions. Areas that were once separated by water might now be connected by dry ground, allowing animals and humans alike to move into new territories. This combination of opportunity and hardship is a recurring theme in Earth's history. Environmental change can close some doors while opening others. The drying Mediterranean basin was no exception. The sun-baked nature of the basin also influenced the chemistry of the soil and air. Salt carried by wind could settle on surrounding lands, altering soil composition and affecting which plants could grow. Over time, this could lead to the spread of salt-tolerant vegetation in some areas, changing the appearance and function of entire landscapes. Dust storms may have been more common, as winds picked up fine particles from the exposed basin floor. These dust clouds could travel long distances, affecting regions far beyond the immediate area. Dust carried through the atmosphere can influence climate by reflecting sunlight and serving as nuclei for cloud formation. In this way, the conditions at the bottom of the basin were not just a local curiosity. They were part of a broader system that connected land, air and water across large parts of the planet. One of the quieter aspects of this story is how it would have felt to experience if anyone had been able to stand there and observe it over time. The basin would have changed slowly enough that no single day would stand out as different from the one before. But over years, decades, and centuries, the transformation would become clear. A shallow pool that once lasted through the summer might dry up earlier each year. A patch of vegetation might retreat toward a riverbank. A migration route might shift slightly, favouring a different path across the plain. These small changes, repeated and accumulated, would reshape the living world in subtle but lasting ways. The idea of a bottom to the world is also an interesting one. In the deep basin, the land was lower than the surrounding regions by hundreds of meters. From many vantage points, the horizon would have been defined by steep slopes and distant ridges, rather than a flat line where sea meets sky. This kind of landscape can create a sense of enclosure, even in an open, expansive space. The basin might have felt like a giant bowl, open to the sky but bounded on all sides by higher ground. The sun would rise and set over these distant edges, casting long shadows across the plains and salt flats. During certain times of day, parts of the basin might be in shade while others were still bathed in light, creating shifting patterns of temperature and activity. Animals and people, if present, would learn to move with these patterns, seeking shade and water when the heat became too intense. The deep valleys carved by rivers would add another layer to this experience. Standing at the bottom of one, you might feel sheltered from the wind, surrounded by walls of rock and soil that told their own layered story of past environments. Climbing out of such a valley, you would emerge into a brighter, harsher world, where the sun and wind had more influence. These contrasts between sheltered and exposed, wet and dry, cool and hot, would define life in the basin. Survival depended on understanding and navigating these gradients. In some ways, the basin during this period might be compared to large desert environments today, where life clusters around water sources and follows seasonal patterns. But the Mediterranean basin added an extra layer of complexity because of its geological history and the thick salt deposits beneath its surface. Salt can influence how water moves through the ground. In some areas, it can create impermeable layers that trap water above them, forming underground reservoirs. In others, it can draw moisture out of surrounding materials, making the soil even drier. These effects would have shaped where plants could take root and where water could linger, further influencing the distribution of life across the basin floor. The longer this phase lasted, the more the living world adapted to its unique conditions. Some species might have developed traits that allowed them to tolerate higher salinity or greater temperature swings. Others might have become more mobile, better able to move between water sources as conditions changed. At the same time, the basin was not completely cut off from the wider world. Periodic connections to the Atlantic could bring in new water, new nutrients, and potentially new organisms. These brief moments of reconnection could refresh some areas, creating temporary expansions of habitable space before the drying resumed. This cycle of isolation and connection is a powerful driver of change in ecosystems. It can lead to bursts of diversity followed by periods of loss, shaping the long-term patterns of life in a region. As the basin continued to deepen and fill with salt, the conditions at its bottom became more extreme. The pools of water grew fewer and more concentrated. The salt plains expanded. The river valleys cut deeper. Life did not disappear entirely, but it became more specialized, more localized, more dependent on specific niches. There is something both stark and quietly hopeful in that image. Even in a place defined by absence, by the loss of a sea, the world did not become truly empty. It became different. If you pause here for a moment, you might find yourself thinking about the environments we see today that feel harsh or unwelcoming. Deserts, salt flats, high mountains, deep ocean trenches, all of them host life that has found a way to persist in conditions that seem, at first glance, almost impossible. The Mediterranean basin during its dry phase was one of those environments on a grand scale. It was a reminder that life does not require comfort. It requires opportunity, however small, and the ability to adapt to whatever circumstances arise. Long after the waves had withdrawn and the basin had settled into its new dry rhythm, something quietly remarkable began to happen in the scattered pockets of water that still clung to the Mediterranean's lowest places. The world around them had changed. The air was hotter and drier. The ground was layered with salt and dust. Rivers cut deep, narrow paths instead of spreading out across wide, gentle plains. And yet, in these remaining pools, channels, and isolated basins, life did not simply fade away. It waited. Waiting in this sense does not mean standing still. It means adjusting to conditions that feel temporary, even if they last longer than any single lifetime. It means surviving in a form that may not look like what came before, shaped by the demands of salt, heat, and isolation. The creatures that lingered in these last refuges of water were not just holding on, they were becoming something new. Imagine one of these pockets, perhaps fed by a river that still found its way down into the deep basin. The water here would not have been like the open sea. It might be cloudy with sediment, heavy with dissolved minerals, and prone to rapid changes in level and chemistry. A period of rain upstream could make it fresher and deeper. A long stretch of dry weather could turn it into a shallow hypersaline pool. Only certain kinds of life can tolerate that kind of instability. These are the organisms that tend to appear at the edges of what seems possible. Some are so small they can only be seen under a microscope. Others are larger, but still carry a sense of being out of place, like visitors from a different world. Microbes would have been among the most persistent inhabitants. Bacteria and archaea that thrive in salty environments, known today as halophiles, are capable of living in conditions that would dehydrate or poison most other forms of life. They can survive in water so saturated with salt that crystals begin to form along the edges. These microorganisms often produce pigments that give their colonies bright colours, reds, oranges, and purples that stand out sharply against pale salt flats. If you had stood at the edge of one of these pools, you might have seen streaks or patches of colour spreading across the surface or clinging to damp ground. A quiet, vivid signal that life was still present in a place that otherwise felt stripped down to its bare essentials. Algae too can adapt to a wide range of salinities. Some species are capable of photosynthesis in water that swings from nearly fresh to intensely salty over short periods of time. These algae form the base of small, self-contained food webs, supporting tiny invertebrates that feed on them, which in turn can support slightly larger predators. Among these invertebrates, you might find creatures similar to brine shrimp, which today live in hypersaline lakes around the world. These small, translucent animals are remarkably resilient. They can survive in water that is many times saltier than the ocean, and their eggs can remain dormant for long periods, waiting for favourable conditions to return. Dormancy is one of the quiet strategies that makes waiting possible. Many organisms produce resting stages, seeds, spores, or cysts that can endure heat, dryness, and chemical extremes. When water returns, even briefly, these dormant forms can awaken, grow, reproduce, and then return to a waiting state when conditions deteriorate again. In this way, life in the basin became a rhythm of appearance and disappearance, tied closely to the presence or absence of water. After a period of rain or a temporary inflow from the Atlantic, shallow lakes might bloom with activity. Algae would spread, invertebrates would hatch and multiply. Birds might arrive to feed on the sudden abundance. Then, as the water evaporated and the salt concentration rose, much of that visible life would fade away. What remained would be the dormant stages tucked into the mud or salt crust, ready to begin the cycle again the next time water returned. This pattern creates a kind of time capsule. Layers of sediment and salt can trap these dormant forms, preserving them in place for long periods. Even millions of years later, scientists can sometimes find microscopic remains in ancient deposits, offering glimpses into the kinds of organisms that once lived in these extreme environments. In the deeper parts of the basin, where water may have persisted for longer stretches, the situation would have been slightly different. These areas might have supported more complex communities of organisms adapted to high salinity and low oxygen. Certain fish species today can survive in brackish or salty lakes, and it is possible that similar creatures found refuge in these deeper pockets during the Mediterranean's dry phase. These isolated populations would have been cut off from the wider marine world. No regular exchange of individuals, no steady flow of new genes. Over time, this kind of isolation can lead to divergence, as populations adapt to the specific conditions of their environment. Some traits that might have been favoured include tolerance for low oxygen levels, the ability to regulate internal salt concentrations more effectively, and behaviours that reduce energy use during periods of stress. These adaptations could make the creatures that lived here look and behave quite differently from their open ocean relatives. But isolation is a double-edged condition. It can encourage specialisation, but it also increases vulnerability. A sudden change in water chemistry, a prolonged dry period, or the loss of a river's flow could wipe out an entire isolated population. Waiting in this sense was always risky. Above the water, on the basin floor and along the surrounding slopes, the presence of these strange temporary ecosystems would have attracted visitors. Birds, in particular, are drawn to shallow water and the invertebrates that often thrive there. Migratory species might have used these pools as stopover points, resting and feeding before continuing their journeys. These birds could also play a role in spreading life from one pocket of water to another. Eggs or spores can cling to feathers or feet, hitching a ride across dry stretches of land. In this way, even isolated pools could remain connected in subtle, biological ways. Mammals and other land animals might have approached these water sources cautiously. The basin floor, with its salt crusts and open spaces, offered little cover. Predators could see from a long way off. The deep river valleys provided more shelter, and these too might have been routes for animals moving between regions. For early human ancestors, if they were present in nearby areas at the time, these water pockets would have been valuable landmarks. Knowing where to find water in a harsh landscape can be the difference between survival and failure. Over generations, such knowledge becomes part of a cultural memory, passed down through experience and practice. The waiting of these creatures was not just about surviving the present, it was also about being ready for a future that, from a geological perspective, was already on its way. The basin, even as it lay dry and layered with salt, was quietly changing in ways that made a dramatic return of the sea more likely. The weight of the salt deposits caused parts of the basin floor to sink. The difference in height between the Atlantic and the Mediterranean basin grew larger. The narrow western connections, though fragile, remained potential pathways for water. In this context, every organism that persisted in the basin was living in a kind of extended anticipation. Conditions were harsh, but not necessarily permanent. The landscape carried the memory of water in its shape. Valleys, channels, and low points all pointed toward a time when flow would return. Some of the life forms in these pockets may have retained traits that made it easier for them to rejoin a marine environment. For example, species that could tolerate a wide range of salinities would be better prepared for the sudden influx of less salty Atlantic water. This idea of waiting is also reflected in the geological record. The layers of sediment and salt often show signs of brief, repeated wet phases. Each one represents a moment when water returned, if only partially, and life had a chance to expand before retreating again. Over time, these cycles could act as a kind of rehearsal for the eventual full return of the sea. Organisms that survived these fluctuations would be the ones most likely to take advantage of a more permanent change when it finally arrived. The concept of strange creatures in this story does not necessarily mean monstrous or alien in appearance. It often means unfamiliar in context. A small crustacean swimming in a shallow, salt-saturated pool at the bottom of a vast basin might look ordinary enough under a microscope, but its existence in that place at that time speaks to a set of conditions that are far from ordinary. The same can be said for the microbial mats that might have coated damp ground, or the algae that bloomed in brief windows of opportunity. These forms of life were part of an ecosystem that existed in the margins, shaped by extremes rather than stability. There is something quietly compelling about that idea. Life not just surviving, but maintaining a foothold in a place defined by absence. The sea was gone, but the memory of it lived on in the chemistry of the water, the shape of the land, and the adaptations of the organisms that remained. it also invites a broader reflection on how life on Earth responds to change. Throughout the planet's history, environments have shifted dramatically. Ice ages have come and gone. Oceans have opened and closed. Continents have collided and separated. In each case, some forms of life have disappeared, while others have adapted, moved, or persisted in small refuges. These refuges become sources of renewal when conditions improve. The Mediterranean basin during its dry phase can be seen as one of these refuges on a grand scale. Not a single sheltered valley or isolated lake, but an entire region transformed into a network of small, scattered habitats that held on to life while waiting for a larger change. The waiting was not passive, it involved constant adjustment. A pool that was habitable one year might be too salty the next. A river that flowed reliably for decades might dwindle or shift its course. The creatures that lived here had to be flexible, able to take advantage of good conditions quickly and endure the bad ones without exhausting their limited resources. In modern environments, we can see echoes of this in places like salt flats, seasonal wetlands, and desert oases. These are areas where life often appears suddenly, flourishes briefly, and then recedes, leaving behind dormant forms that hold the potential for the next cycle. The basin would have been a vast version of that pattern, with life appearing and disappearing across a landscape the size of a sea. One of the more intriguing possibilities is that some of these organisms, adapted to extreme conditions, might have left a lasting legacy in the region's biology. When the Mediterranean refilled, the returning water would have mixed with the organisms already present in the basin. This could have led to a blending of life forms from the Atlantic and from the isolated basin, creating new combinations and interactions. Species that had evolved under hypersaline or low oxygen conditions might have found new niches in the re-established sea, influencing the composition of its ecosystems. While it is difficult to trace these connections directly after millions of years, the idea highlights how periods of isolation and reconnection can shape the long-term patterns of life in a region. As the basin continued to wait, the physical landscape around these pockets of life also evolved. The salt layers beneath the surface began to deform under their own weight, creating subtle changes in the topography. The deep river valleys continued to widen and deepen in places, shaping the paths that water would one day follow back into the basin. These changes meant that when the sea eventually returned, it would not be flowing into the same shape it had left behind. The basin had been remodeled by absence, and that remodeling would influence how water, sediments, and life would move and settle in the future. For the creatures waiting in the basin, this meant that the return of the sea would not simply restore the old world. It would create a new one, with new coastlines, new depths, and new patterns of circulation. The waiting, in that sense, was also a period of preparation for a different kind of future. If you imagine standing at the edge of one of these remaining pools during a quiet moment, you might see little to suggest the scale of the story unfolding around you. The water might ripple gently in a light breeze, insects might skim the surface, the sun might cast long shadows across the salt-crusted ground. It would feel small, local, immediate. And yet, beneath that small scene, beneath the thin layer of water and the crust of minerals, lay the record of a vast transformation. Above it, in the distant west, lay an ocean held back by a narrow, fragile boundary. The creatures in that pool, from the tiniest microbes to the birds that visited from above, were part of a story that stretched across continents and millions of years. They were living in the pause between two very different worlds, one defined by the absence of a sea and the other waiting quietly to return. Let that image rest with you for a moment. A vast, quiet basin under an open sky. Pockets of water shining in the low points. Tiny forms of life moving, growing, and waiting in the margins. And beyond the distant ridges, an ocean pressing gently, persistently, against a boundary that will not hold forever. Beneath the surface of the modern Mediterranean, under the steady movement of waves and the soft shifting of currents, there is a world that most people never think about. It is not made of coral reefs or shipwrecks or schools of fish gliding through blue water. It is made of something far quieter, far heavier, and far older. There are mountains of salt down there. Not hills or thin layers, but vast thick formations that rise and fold beneath the seafloor, hidden under kilometres of water and sediment, carrying the memory of a time when the sea itself was absent. It can feel strange to imagine salt as something that builds landscapes. In everyday life, salt is a small, familiar thing. It sits in a shaker on a table. It dissolves easily in water. It sprinkles across food and disappears into flavour. But on a geological scale, salt behaves very differently. Given enough time and enough material, it becomes a structural force, a substance that can shape the earth from below. The story of these hidden salt mountains begins with all those quiet moments when crystals drifted down through the shrinking waters of the Mediterranean basin. Layer after layer they settled. Gypsum first, then halite, then more complex minerals as the chemistry of the remaining water changed. Over thousands of years those layers thickened. Over tens of thousands of years they became massive. Over hundreds of thousands of years they turned into a foundation that would influence everything that came after. When the Mediterranean eventually refilled, those salt layers did not vanish. They were buried. Water rushed back in, filling the deep basin, covering the mineral plains, drowning the river valleys, and laying down new layers of sediment on top of the salt. Mud, sand, and organic material settled out of the water and formed a blanket over the crystalline deposits. Over time, that blanket grew thicker, pressing down on the salt below. This is where salt begins to reveal its more unusual side. Most rocks, when placed under pressure, resist. They crack, fracture, or stay rigid. Salt, however, has a different personality. It is soft, at least by geological standards. Under enough weight it can flow. Not quickly, not like water, but slowly, like a very thick, very patient liquid. As more and more sediment piled on top of the buried salt layers, the pressure increased. The salt began to move. It squeezed and shifted, finding paths of least resistance, rising in some places and sinking in others. Over millions of years, this movement created structures that geologists call salt domes and salt ridges, features that can rise hundreds or even thousands of meters within the Earth's crust. So when we talk about mountains of salt hidden beneath gentle waves, we're not speaking metaphorically. These are real, physical structures, massive formations that push up against the layers above them, shaping the seafloor and influencing the geology of the entire region. If you could somehow peel back the water and sediment like layers of fabric, you would see these salt bodies standing out against the surrounding rock. They might look like enormous slow-moving bubbles frozen in place, or like thick columns that have pushed their way upward over unimaginable spans of time. This movement of salt has quiet but powerful consequences. As salt rises, it bends and fractures the layers of rock above it. This can create traps where fluids like oil and gas collect, which is one of the reasons the Mediterranean region has been of such interest for energy exploration. The shape of the salt determines the shape of the spaces around it, guiding where things can move and where they get stuck. It also influences the shape of the seafloor. In some areas, the slow rise of salt domes can create subtle bumps or ridges on the seabed, even under kilometres of water. These features can affect how currents move, how sediments are deposited, and how marine life distributes itself across the bottom. All of this is happening quietly, out of sight, beneath a surface that looks calm and unchanging to anyone standing on a beach or looking out from a boat. There is something deeply layered about this image. On top, there is the modern sea, with its waves, its tides, its familiar blues and greens. Beneath that, there are layers of sediment, recording the return of water, the growth of ecosystems, the slow rain of particles from above. And beneath that, there is salt, thick and heavy, preserving the memory of a world that existed when the sea was gone. These buried deposits are among the strongest pieces of evidence scientists have for the scale of the Messinian Salinity Crisis. You do not get hundreds of meters of salt from a brief drying event. You get it from sustained, repeated cycles of evaporation and mineral deposition over long periods of time. When drilling projects first pulled up cores from the Mediterranean seafloor in the late 20th century, the discovery of these thick salt layers was a moment of quiet revelation. It confirmed that the sea had not just become a little saltier. It had in many places nearly dried out completely. Each core, a narrow cylinder of rock and mineral brought up from deep below, was like a timeline you could hold in your hands. The white and pale layers of salt stood out clearly against darker sediments, marking a period when water had retreated and minerals had taken over. These cores also show that the salt was not a single, uniform layer. It was broken into sequences, separated by thin bands of sediment. This pattern suggested repeated changes in conditions, times when water returned, even briefly, followed by renewed drying. In this way, the hidden salt mountains became a kind of archive, a physical memory of the basin's long and complicated relationship with the sea. What is especially intriguing is how these structures continue to shape the region today. The Mediterranean seafloor is not flat. It is a varied landscape of ridges, basins and slopes. Some of this variation comes from tectonic activity, the same slow movement of plates that helped close the basin in the first place. But some of it is driven by the salt below. As salt flows and shifts, it can create zones of weakness in the crust. These zones can become pathways for earthquakes or influence where faults develop. They can also affect how the seafloor responds to the weight of water and sediment, leading to subtle changes in depth over time. For marine life, these features matter. The shape of the seafloor influences where nutrients collect, how currents move, and where different species can find suitable habitats. A ridge created by a salt dome might become a place where cold, nutrient-rich water is pushed upward, supporting a more productive ecosystem. A basin formed by subsiding layers might trap sediments and organic material, creating a different kind of environment. So even though the salt itself is buried, its presence is still felt in the living patterns of the sea above. There is also a deeper sense in which these hidden mountains connect the present to the past. Every wave that moves across the Mediterranean today does so over a foundation built during a time when there were no waves at all. The sea is, quite literally, resting on the memory of its own absence. This idea can feel a little abstract until you think about it in more familiar terms. Imagine walking across a field that was once a forest. Beneath the soil there might still be remnants of roots, buried leaves, traces of an older landscape. The field you see is real, present, alive, but it is also layered on top of something that came before. The Mediterranean is like that, just on a far larger scale. The salt deposits also help explain why the basin behaves the way it does in response to stress. Because salt can flow, it can act as a kind of cushion or lubricant between layers of rock. In some regions, this can reduce the buildup of stress that leads to earthquakes. In others, it can focus that stress along specific lines, making certain faults more active. Geologists study these patterns to better understand the risks and behaviours of tectonic systems around the Mediterranean, which is one of the most geologically complex and active regions on the planet. Beyond their structural role, the salt layers are also important for understanding the chemistry of the sea. When water flows through or over salt-rich sediments, it can dissolve small amounts of minerals and carry them back into the water column. This can influence the salinity and composition of the surrounding seawater, especially in deeper regions where circulation is slower. This means that the ancient salt, formed during a period of extreme drying, still has a subtle influence on the living sea today. It is a quiet, long-term conversation between past and present. carried out through chemistry and pressure rather than sound and movement. There is something almost comforting about that continuity. The idea that the Earth does not simply move from one state to another and forget what came before. Instead, it carries its history forward, embedding it in layers of rock, in the shape of landscapes, and in the behaviour of systems that continue to operate long after the original conditions have changed. The salt mountains beneath the Mediterranean are one of those embedded memories. If you imagine, for a moment, diving straight down through the water, past the fish and the soft drifting particles of organic matter, past the seafloor and into the layers of sediment, you would be travelling backward in time. Each metre you descend would represent thousands, then tens of thousands, then hundreds of thousands of years. Eventually you would reach the salt, and with it, the record of a world that no longer exists. A world of dry plains, deep valleys, and scattered pools of water. A world where the sea had withdrawn and left behind its dissolved essence in solid form. The fact that this world is still present, in a sense just hidden, adds a certain depth to how we think about landscapes. The surface is only the most recent chapter. Beneath it lies a stack of older stories, each one influencing the shape and behaviour of what comes after. The Mediterranean's hidden salt formations also play a role in how the basin responds to the weight of the water above. The sea is heavy. A column of water several kilometres deep exerts immense pressure on the crust below. Where salt layers are thick and soft, they can deform under that pressure, allowing the seafloor to slowly sink or shift. This process, known as subsidence, can create new basins or deepen existing ones over time. It can also influence how sediments are deposited, creating patterns that scientists can trace back to the movement of salt below. In some places, the rising of salt domes can bring ancient layers of rock close to the surface. These layers might contain fossils or other clues about even older periods in the region's history. In this way, the salt not only records one dramatic episode, but helps reveal others as it moves and reshapes the crust around it. For people who live around the Mediterranean today, all of this is largely invisible. Cities rise and fall, harbours are built and rebuilt, trade and travel move across the water. The presence of salt mountains beneath the sea is not something that enters everyday conversation, and yet their influence is there, quietly shaping the region's geology, its resources, and even its risks. This hidden world also adds another layer to the story of the sea's return. When the Atlantic finally broke through the narrow western barriers and water rushed back into the basin, it did not flow over a simple empty floor. It poured into a landscape already shaped by thick salt deposits and deep river valleys. The water would have dissolved some of the salt as it moved, altering its own chemistry. It would have picked up sediments from the basin floor and carried them into new patterns of deposition. The presence of soft, mobile salt beneath the surface would have influenced how the seafloor responded to the sudden weight of returning water. In this sense, the salt mountains were not just remnants of the dry phase. They were active participants in the rebirth of the sea. There's also something quietly striking about the idea of gentleness on the surface and heaviness below. Waves can look soft, almost playful as they move across the Mediterranean. Sunlight glints off the water. Boats leave delicate trails of foam behind them. But beneath all that, there is a foundation built of dense, ancient minerals, pressing and shifting, shaping the crust in slow motion. The contrast between the lightness of the surface and the weight of what lies beneath is a reminder of how layered and complex even the most familiar places can be. If you find yourself near the Mediterranean at some point, standing on a beach or a cliff overlooking the water, you might try to hold this image in mind. The sound of waves in your ears, the smell of salt in the air, and far below, out of sight, enormous formations of salt that settled there during a time when the sea itself was gone. It can change the way a place feels, adding a sense of depth not just in physical terms but in time as well. Long before any wave returned to the basin, Before any river found itself flowing into a rising sea instead of a deep, dry valley, the ground itself was already at work. Not in sudden jolts or dramatic fractures, but in movements so slow and steady that they would have been invisible to anything living at the time. This was the Earth's crust, the outer shell of the planet, shifting the balance in a way that would eventually decide the fate of an entire sea. To think about the crust is to think about something that feels solid and permanent. We walk on it, we build on it, we carve cities and roads into it and assume it will stay where it is. But on a geological timescale, the crust is more like a collection of drifting platforms, thick slabs of rock that float on a softer, hotter layer beneath. These slabs, known as tectonic plates, are always moving, even when everything above them feels perfectly still. The Mediterranean region sits at one of the most complex and restless boundaries on the planet. It lies between the African plate to the south and the Eurasian plate to the north, with smaller plates and fragments caught in between. This is not a simple edge where one plate neatly slides past another. It is a crowded, tangled zone where pieces of crust collide, sink, rise and twist in response to deep forces coming from inside the Earth. During the time when the Mediterranean basin was drying and filling with salt, this tectonic dance did not pause. In fact, it played a central role in shaping what was happening at the surface. Africa continued its slow journey northward, pressing into Europe. This collision did not happen all at once or in a straight line. Instead, it created a patchwork of compression in some areas and stretching in others. Mountains rose in certain regions, basins sank in others, narrow passages between land masses became shallower, deeper, wider, or narrower, depending on how the crust beneath them responded. One of the most important areas affected by this movement was the western gateway between the Atlantic and the Mediterranean. The region that would become the Strait of Gibraltar sat on a piece of crust that was being squeezed and uplifted by the slow convergence of the plates. Sediments piled up. Land rose. What had once been a broad, open connection became a more fragile, shallow pathway. This uplift did not need to be dramatic to have a major effect. A change of just a few tens of meters in elevation could alter how water flowed between the ocean and the basin. In a system already sensitive to evaporation and water balance, that kind of change was enough to tip the scales. At the same time, other parts of the Mediterranean region were doing the opposite. While some areas rose, others sank. The weight of the accumulating salt and sediment in the basin pressed down on the crust, causing it to subside. This created a deeper depression, increasing the difference in height between the basin floor and the level of the Atlantic. This difference in height is a quiet but powerful concept. Water, guided by gravity, always wants to move from higher ground to lower ground. The greater the difference in elevation, the more potential energy is stored in the system. During the dry phase, this potential energy was building up, even though the narrow western gateways prevented it from being released. So in one part of the system, the crust was rising, closing off the connection. In another, it was sinking, deepening the basin. Together, these movements were setting the stage for a dramatic change in the direction of water flow. But the crust does not move in simple straight lines. It bends, warps, and fractures in complex ways. In some places, the pressure of colliding plates caused sections of crust to fold upward into mountain ranges. The Alps, the Apennines, and the mountains of North Africa all owe their existence in part to this long history of compression. In other areas, the crust was pulled apart. This stretching can create rift zones and basins, where the land sinks and makes room for sediments and eventually water. Parts of the Mediterranean seafloor show signs of this kind of extension, with deep basins formed by the crust thinning and dropping down. These contrasting movements created a landscape of highs and lows, both above and below the surface. They influenced where rivers flowed, where sediment accumulated, and where water could collect or escape. If you imagine looking at the region from very far away and very far back in time, you might see the crust behaving like a slow, uneven breathing motion. some areas gently rising, others slowly sinking, the pattern changing over millions of years as forces from deep within the Earth continued their steady work. One of the more subtle effects of this movement is how it influenced the shape and stability of the salt layers beneath the basin. As the crust bent and shifted, the pressure on the buried salt changed. In areas where the crust subsided, the salt was squeezed more tightly, encouraging it to flow and form domes and ridges. In areas where the crust rose, the pressure might ease slightly, allowing the salt to settle into different shapes. This interaction between crust and salt added another layer of complexity to the system. The salt was not just a passive layer being carried along by the movement of rock. It was an active material, responding to pressure and in turn influencing how the crust above it behaved. Over long periods, this feedback loop could change the shape of the basin itself. A rising salt dome might push up the seafloor, creating a ridge. A sinking area might become a deeper pocket, collecting more sediment and water when the sea eventually returned. All of this was happening while the basin lay dry or partially dry, its surface defined by salt flats, river valleys, and scattered pools of water. The landscape that would eventually be flooded again was being quietly remodelled from below. The eastern side of the Mediterranean also played a role in this shifting balance. The region between what is now Greece, Turkey, and the Middle East is a mosaic of smaller plates and fragments. These pieces of crust moved in different directions, sometimes colliding, sometimes sliding past each other. This complex motion influenced the connections between the Mediterranean and other basins to the east. Shallow seas and lakes in this region could open or close depending on how the land rose or sank. These changes affected how much water and sediment could move into or out of the Mediterranean from that direction. While the western gateway to the Atlantic was the most important connection for maintaining the sea's overall water balance, the eastern connections added their own layers of variability. They could influence regional salinity, circulation patterns, and the distribution of life during both the dry and wet phases. It is easy to think of the Earth's crust as a background stage on which other processes play out. But in this story, the crust is one of the main characters. Its movements, though slow and subtle, determined the boundaries within which everything else happened. There is a certain elegance in this. The same forces that raise mountains and create earthquakes also decide whether a sea can exist. The same pressure that folds rock can close a passage for water. The same weight that sinks a basin can prepare it to receive an ocean. One way to understand this balance is to think of the Mediterranean system as a kind of scale. On one side, you have the Atlantic Ocean, heavy with water pressing toward the basin. On the other, you have the basin itself, deep and empty, pulling downward. Between them, you have a narrow region of crust that can rise or fall, opening or closing the path between the two. For a long time, during the Messinian period, that middle region stayed just high enough to keep the balance tipped toward dryness. The basin lost more water than it gained. Salt accumulated, rivers cut deeper, life adapted to a sun-baked world. But the crust never stopped moving. The forces that had lifted the Western Gateway were not permanent. Over time, erosion, continued tectonic adjustment, and the sheer weight of accumulated sediments could weaken and lower parts of the barrier. In some areas, the crust might have fractured, creating zones of weakness. These fractures could become pathways for water once the pressure difference between the Atlantic and the basin became large enough. This is where the idea of quiet shifting becomes especially important. There may not have been a single dramatic event, like a massive earthquake that suddenly opened the gate. Instead, the barrier may have been gradually worn down, thinned, and weakened until it could no longer hold back the water. Imagine a dam made of loose earth rather than concrete. At first, it stands firm, holding back a lake. Over time, small leaks appear. Water seeps through. The material becomes saturated and less stable. Eventually, a section gives way, and the water rushes through. The crustal barrier between the Atlantic and the Mediterranean may have behaved in a similar way, though on a scale far larger and over a much longer period of time. As the barrier weakened, the system became increasingly sensitive. The difference in height between the Atlantic and the basin was now immense. Even a small opening could allow a significant flow of water to begin. Once that flow started, it would not remain small for long. Water is very good at enlarging its own pathways. A trickle can become a stream. A stream can become a torrent. The more water that flows through an opening, the more it erodes the material around it, making the opening larger and allowing even more water to pass. This positive feedback is one of the reasons the eventual return of the sea is thought to have been so dramatic. But before we get there, it is worth lingering a little longer on the quiet phase, when the crust was still doing its slow, patient work. In the surrounding regions, the shifting crust also influenced climate and ecosystems. Rising mountains can block wind patterns and change where rain falls. Sinking basins can collect water and create new lakes or wetlands. These changes would have affected the distribution of plants and animals across Europe, North Africa, and the Middle East. Over long periods, these shifts can shape entire biogeographic regions, influencing which species are found where and how they move between continents. The Mediterranean region, even today, is known for its diversity of landscapes and ecosystems, from arid deserts to lush coastal plains to high mountain ranges. Much of this diversity has its roots in the long, complex history of crustal movement and environmental change. During the Messinian period, this diversity would have been expressed in different ways, with some areas becoming harsher and more isolated, while others remained relatively hospitable. The idea that the crust was quietly shifting the balance also applies to the way sediment moved through the system. As mountains rose, they were eroded by wind, rain, and ice. The resulting sediment was carried by rivers into the basin, adding to the layers of material on the basin floor. This sediment not only buried the salt layers, but also added weight to the crust, contributing to further subsidence. This in turn deepened the basin even more, increasing the potential energy of the system. So, there was a loop at work here. Tectonic forces shaped the land, which influenced erosion and sedimentation, which changed the weight on the crust, which influenced how the crust moved. This kind of feedback is common in Earth systems. Processes do not operate in isolation. They interact, amplify, and sometimes counteract each other in ways that can lead to unexpected outcomes. In the case of the Mediterranean, the outcome was a basin that became deeper, a barrier that became more fragile, and a growing imbalance between ocean and basin that could not last forever. There is a certain quiet tension in this phase of the story. Everything is moving, but nothing has yet reached its breaking point. The basin lies dry and layered with salt. The rivers continue to cut their deep paths. The crust continues to rise here and sink there. Above it all, the Atlantic Ocean presses against the western boundary, its surface level far higher than the floor of the basin on the other side. The difference between them is like a stretched string, held in place by a narrow, weakening section of land. For the living world around the basin, this tension is not something that can be seen or felt directly. Life goes on in its adapted forms, in river valleys, in scattered pools, in salt-tolerant communities. But in the deep structure of the planet, the conditions for a dramatic change are steadily being prepared. This way of thinking about change as something that builds quietly, rather than arriving suddenly, can feel counterintuitive. We often imagine major events as things that happen in an instant. A flood, an eruption, a collapse. But in many cases, the instant is just the visible release of energy that has been accumulating for a very long time. The Earth's crust, with its slow, patient shifting, is one of the great accumulators. It stores stress, pressure, and imbalance in the shape of landscapes and basins. When that stored energy finally finds a path to release, the result can be swift and dramatic. In the Mediterranean story, the release is still ahead of us. The quiet phase of crustal movement is nearing the point where it can no longer hold the system in its dry state. For now, though, we remain in this moment of poised balance. The basin is deep and empty. The salt is thick and heavy beneath layers of sediment. The barrier to the west is fragile but still standing. The ground beneath it all continues to move, almost imperceptibly, guided by forces that originate far below the surface in the slow, convecting heat of the Earth's interior. If you let this image settle, you might find it changes the way you think about the ground beneath your own feet. The street, the floor, the landscape around you. All of it rests on a crust that is never truly still. It may not move in ways you can see or feel from one day to the next, but over long stretches of time, it reshapes continents, opens and closes seas, and sets the stage for stories as large as the disappearance and return of an entire ocean basin. For a long time, nothing much seemed to happen. The basin lay open beneath the sky, its floor layered with salt and sediment, its deep valleys carved by rivers that still followed their steep, determined paths. The air moved across the plains, lifting dust and fine grains of mineral, carrying them toward the surrounding highlands. The remaining pools of water shimmered in low places, sometimes growing, sometimes shrinking, depending on the rhythm of rain, river flow, and the fragile connections to distant seas. This was the long silence before the flood, not a silence of absolute stillness, but a silence of waiting. It is easy to imagine this period as empty, as a pause in the story where nothing of consequence unfolds. But in reality, this was one of the most important phases of all. The dramatic return of the sea when it came would not be an isolated event. It would be the release of a tension that had been building for hundreds of thousands of years. The quiet, patient work of this silent phase was what made that release possible. Picture the basin at this time as a vast, shallow bowl carved into the land. Its lowest points lay far below the level of the Atlantic Ocean, separated from it by a narrow, fragile stretch of land to the west. That difference in height was not just a number on a geological chart, it was stored energy. Water on one side of the barrier stood higher than the land and salt flats on the other. Gravity, constant and unrelenting, was waiting for a chance to act. But the barrier still held. On the surface, the region might have felt steady, even predictable. Seasons would come and go. Periods of rain would green the river valleys for a time. Dry spells would return the plains to pale, reflective expanses of salt and dust. Birds would arrive and depart. Animals would follow familiar routes between water sources. Life, in its own way, had settled into the rhythm of this altered world. The silence, though, was not just in the landscape. It was also in the movement of water between the Atlantic and the basin. The once active exchange that kept the Mediterranean alive as a sea had been reduced to little more than a memory. If any water still passed through the Western Gateway, it did so in small, limited amounts, not enough to change the overall balance. The basin had become, for all practical purposes, isolated. This isolation shaped everything. The chemistry of the remaining water bodies, the composition of the air above the basin, the movement of sediments and dust, the patterns of life that could persist in such a place. Even the rivers which continued to deliver fresh water from distant mountains and plains were part of this quiet phase. They flowed, they eroded, they deposited, but they did not change the fundamental fact that the basin was lower than the sea beyond the barrier. Each drop of water that entered the basin from a river eventually left again, not by flowing out to the ocean, but by lifting into the air through evaporation. The system was closed, cycling water within its own boundaries. This kind of closed basin is a powerful thing. It becomes its own world, governed by internal feedbacks rather than by exchange with the wider ocean. Small changes can have large effects because there is no external system to absorb or balance them. A slightly warmer climate can lead to more evaporation, which increases salinity, which changes how water moves and how life responds. A slightly cooler or wetter period can freshen some areas, allowing brief expansions of habitable space before the drying resumes. These internal cycles can repeat again and again, creating a pattern of subtle variation within an overall state of isolation. The salt layers beneath the surface continued to grow during this time, though not always at the same rate or in the same way. In some periods, thick deposits formed, suggesting long stretches of intense evaporation. In others, thinner layers indicate brief returns of water or increased river input. Each layer added weight to the basin floor. That weight pressed down on the crust, causing further subsidence. The basin, in response, grew deeper. This deepening was not something that could be seen from one year to the next, or even from one century to the next. But over the long silence of this phase, it became significant. The difference in elevation between the Atlantic and the basin increased. That difference was like a growing reservoir held back by a narrowing dam. The Western Barrier, meanwhile, was not a static wall. It was a stretch of land shaped by the same forces that were reshaping the rest of the region. Erosion from wind and rain wore away at its surface. Rivers flowing toward the Atlantic cut into its slopes from the other side. Tectonic movements continued to bend and fracture the crust beneath it. Small cracks and low points could develop, even if they did not yet form a continuous path for water. These weaknesses mattered. They were the seeds of what would eventually come. The idea of silence in this context is not just about the absence of dramatic events. It is also about the absence of connection. The basin, cut off from the open ocean, was living in a kind of geological solitude. Its story was unfolding inwardly, shaped by what happened within its own boundaries rather than by exchange with the wider world. This kind of isolation can lead to a sense of stasis, even when change is happening all the time. The landscape might look much the same from one generation to the next. The same river valleys, the same salt plains, the same distant ridges framing the horizon. But beneath that familiar surface, the system was becoming more and more unbalanced. The Atlantic, on the other side of the barrier, did not share in this quiet. It continued its vast circulation, driven by winds, tides, and the rotation of the planet. Water moved between hemispheres, between polar regions and the tropics, carrying heat, nutrients, and life across enormous distances. In comparison, the Mediterranean basin during this phase was a closed loop, its water cycling between ground and sky, its chemistry slowly drifting away from that of the open ocean. The contrast between these two systems is striking. One open, connected, and dynamic on a global scale. The other isolated, inward, and defined by its own internal processes. And between them, a narrow stretch of land that held back a difference in water level, measured not in centimetres, but in hundreds of metres. The long silence before the flood was, in a sense, the time when this contrast became most extreme. For the living world around the basin, this period of waiting would have felt normal. Animals and plants adapt to the conditions they experience, not to the conditions that came before or the ones that will come after. A generation born into a dry basin does not know what it means to live beside a sea. The memory of waves, tides, and open water would have been written only in the shape of the land, in the curves of ancient shorelines carved into rock, in the wide, flat terraces that once lay just below the surface of the sea, in the deep valleys where rivers had cut down to reach a distant, vanished shoreline. These features would have been silent witnesses to a different world. If you stood at the edge of the basin during this time, looking out across the salt flats and distant pools, you might have noticed these shapes without knowing what they meant. A gentle slope that seemed out of place, a line of rock that ran across a hillside like a faint horizontal scar. These were the traces of water's former reach. The long silence was also a time when the atmosphere and climate of the region adjusted to the absence of a large body of water. Without the moderating influence of the sea, temperatures could swing more widely. Summers might be hotter, winters cooler. Rainfall patterns could shift, becoming more seasonal or more irregular. These changes would have influenced not just the basin itself, but the surrounding lands. Vegetation patterns might have shifted. Grasslands could expand or contract. Forests might retreat toward higher or wetter areas. In this way, the silence of the basin was not confined to its own boundaries. It echoed outward, shaping regions far beyond its dry floor. The rivers, too, were part of this extended influence. Their deep valleys became corridors that linked distant uplands to the basin. Sediments carried down these paths recorded changes in climate and erosion far upstream. A period of heavy rainfall in the mountains could send a pulse of sediment into the basin, layering new material over the salt flats. A long dry spell could reduce river flow, allowing evaporation to dominate and salt to settle once more. These pulses created a rhythm in the geological record, a pattern of alternating layers that scientists can read millions of years later. During the long silence, this rhythm became a kind of heartbeat for the basin, steady and internal, disconnected from the larger oceanic system beyond the Western Barrier. There is a certain stillness in this image that can feel almost calming, even though it represents a time of extreme conditions. A vast, quiet landscape under a wide sky, slow-moving rivers in deep valleys, pale plains that reflect the sun, life clustered in pockets and corridors, and above it all, a sense of waiting that is not conscious, not aware, but built into the very structure of the land and water. The idea of waiting is interesting when applied to a planet. The Earth does not plan. It does not anticipate. It follows physical laws, responding to forces and conditions as they arise. And yet, from our perspective, it can feel as though the basin was waiting for the right moment, the right set of circumstances for the sea to return. That moment depended on many things coming together. The barrier to the west needed to weaken. The difference in height between ocean and basin needed to grow large enough. The crust needed to shift in just the right way to create a path for water. During the long silence, all of these conditions were being prepared. The barrier was being worn down by erosion and stress. The basin was sinking under the weight of salt and sediment. The Atlantic continued to press against the boundary, its water level held high by the vast connected system of the world's oceans. This combination created a system that was increasingly unstable, even if it looked calm on the surface. There is a parallel here to many kinds of change, both in nature and in human experience. Long periods of apparent stability can hide slow, accumulating shifts beneath them. When the visible change finally comes, it can seem sudden, even though it has been building for a very long time. The long silence before the flood is a reminder of that quieter side of transformation. If you imagine standing in the basin during this time, perhaps at night, the experience might feel especially still. The sky would be wide and clear, stars visible without the haze of moisture rising from a nearby sea. The air might cool quickly after sunset, creating a sharp contrast with the heat of the day. The salt flats could glow faintly in moonlight, their pale surfaces reflecting the sky. The deep river valleys would lie in shadow, their presence hinted at by the sound of distant water or the movement of air. In such a moment, it would be hard to believe that this quiet world was on the verge of a change that would reshape it entirely. The idea that an ocean could one day rush back into this empty space might feel almost impossible to imagine. The basin feels too large, the barrier feels too solid, the silence feels too complete, and yet the physical conditions were lining up in a way that made that outcome more and more likely. The weight of the Atlantic, held back by a narrow stretch of land, was a constant pressure. The deeper the basin became, the greater the potential energy of that pressure. At some point, the balance between the strength of the barrier and the force of the water would tip. What is fascinating is that this tipping point did not require a dramatic trigger in the way we often think of such events. It did not necessarily need a massive earthquake or a sudden collapse. It could begin with something much smaller. A low spot eroded a little further. A crack widened by a little more. A river on the Atlantic side cut a little deeper into the barrier. Once a small channel formed, water could begin to flow, and once water began to flow, it could rapidly enlarge its own path, turning a small opening into a much larger one. This is why the long silence is so important to the story. It is the phase when the system became primed for rapid change. Everything that happened during this time, the accumulation of salt, the deepening of the basin, the weakening of the barrier, contributed to the intensity of what would follow. In that sense, the silence was not empty. It was full of preparation. For the life forms waiting in their scattered refuges, this preparation was invisible. They continued their cycles of growth, dormancy, movement and survival, responding to the conditions of the moment rather than to the hidden tension in the landscape. For the rivers, it was business as usual. They flowed, they eroded, they deposited, shaping their valleys and carrying the story of distant climates into the basin. For the crust, it was a continuation of a much longer pattern of movement, pressure and release that has shaped the planet for billions of years. All of these processes overlapped in the long silence, creating a layered, interconnected system that was far from static, even if it looked that way on the surface. There is something quietly powerful in that idea, a reminder that stillness and motion are not always opposites, that a calm surface can hide a great deal of activity beneath it. There was no announcement, no signal sent across the sky to mark the moment when the balance finally tipped. The Atlantic did not wait for permission. It did not hesitate. It simply followed gravity, the same quiet rule that had guided rivers down into the basin for so long. After hundreds of thousands of years of pressure building up behind a narrow, fragile barrier, water found a path. At first, it may have been nothing more than a trickle, a low point in the land, a crack widened just enough, a shallow channel deepened by erosion from rain or river flow on the ocean side. Through that small weakness, a thin stream of Atlantic water began to move eastward, down toward a place that lay far below the level of the open sea. Even a trickle carries energy when the drop is large enough, and in this case, the drop was immense. The Mediterranean basin, carved deep by subsidence and layered with salt and sediment, lay hundreds of meters, perhaps more than a kilometer, below the surface of the Atlantic. The difference in height between the two bodies of water was like a stretched spring. Once released, it did not gently unwind. It snapped forward. The first flow of water would have carved at the barrier almost immediately. Moving water erodes the ground beneath it, especially when it is travelling downhill with speed and force. What began as a narrow channel would have widened and deepened rapidly, allowing more water to pass through. More water meant more erosion. More erosion meant an even wider opening. This is one of the most powerful feedbacks in nature. Flow creates space. Space allows more flow. The process feeds on itself. Within a short period of time, perhaps days, weeks, or months rather than years, the trickle would have grown into a stream, the stream into a torrent, and the torrent into something that no longer resembled a river at all. What rushed into the Mediterranean basin was not just water. It was the weight and momentum of an entire ocean, pouring downhill into a vast empty depression. Imagine standing at the edge of the newly opened channel during those first moments of full connection. The sound alone would have been overwhelming. Not the soft crash of waves on a beach, but a deep, continuous roar, the kind of sound that fills the air and vibrates through the ground. The water would have been moving at tremendous speed, driven by gravity and the sheer difference in elevation. It would have torn at the rock and soil beneath it, carrying away huge amounts of material and reshaping the landscape in real time. Downstream in the basin itself, the effect would have been just as dramatic. The dry valleys and salt flats that had defined the region for so long would have been met by a wall of water, advancing across the floor of the depression. This was not a gentle return of the sea. It was a flood on a scale that is difficult to fully picture. Some scientists describe this event as one of the largest known waterfalls in Earth's history. The Atlantic, spilling over the edge of the Western Barrier, would have plunged into the basin below, creating a vertical drop of hundreds of meters. The volume of water passing through this opening could have been millions of cubic meters per second, far greater than any river flowing on the planet today. The falling water would have created a massive churning pool at the base of the drop, a turbulent foaming zone where air and water mixed violently. Mist and spray would have risen into the sky, carried by winds that could spread moisture far into the surrounding dry landscape. The basin, which had been defined by heat, salt, and dust, would suddenly have known humidity, clouds, and the steady presence of moving water once again. As the flood advanced, it would have followed the lowest paths first. The deep river valleys carved during the dry phase became natural channels for the returning sea. Water rushed down these steep corridors, filling them from the bottom up, turning canyons back into underwater valleys. Plains that had been dry and reflective for thousands of years were submerged. Salt crusts dissolved into the water, changing its chemistry as it spread. Sediments were picked up and carried along, creating plumes of murky water that drifted outward from the advancing front. The speed of this filling is one of the most striking aspects of the event. While the drying of the Mediterranean took hundreds of thousands of years, the refilling may have happened in a matter of months to a few years. A transformation that had unfolded slowly and quietly was reversed in a rush. If you imagine the basin as a giant bowl, the Atlantic was now being poured into it at a rate that far outpaced anything the region had experienced before. The water level rose day by day, perhaps even hour by hour, climbing up the sides of the basin and reclaiming the land that had been exposed for so long. The shoreline, which had been far out on the basin floor, began to move inward, climbing the slopes toward its modern position. Valleys disappeared beneath the rising water. Oases and pools were swallowed and merged into a growing connected body. For the life forms waiting in those scattered pockets, this moment would have been both an end and a beginning. Fresh, less salty Atlantic water mixed with the hypersaline waters of the basin. The chemistry of the environment changed rapidly. Organisms adapted to extreme salinity might have struggled as conditions became more moderate. Others, better suited to open marine conditions, would have found new opportunities as the sea expanded. Plankton carried in from the Atlantic would have spread across the basin, forming the base of new food webs. Fish and invertebrates followed, either swimming in through the newly opened gateway or emerging from refuges within the basin itself. The returning sea did not simply erase what had come before, it blended with it. The thick salt layers on the basin floor were partially dissolved by the incoming water, adding to the salinity of the newly formed sea. This is one of the reasons the Mediterranean today is saltier than the Atlantic. Its past, quite literally, still flavours its present. The sediments carried by rivers during the dry phase were reworked by waves and currents, reshaped into new deltas, beaches and underwater slopes. The deep canyons carved by rivers became submerged valleys, guiding currents and influencing where sediments would settle in the future. The hidden salt mountains beneath the surface also played a role. As the weight of the returning water pressed down on the basin, the salt layers responded by shifting and flowing, subtly changing the shape of the seafloor over time. This interaction between water, sediment and salt added another layer of complexity to the reborn sea. The flood itself would have been a powerful agent of erosion and transport. The water rushing in through the western gateway would have carried enormous amounts of material into the basin. Rock fragments, sand and soil torn from the barrier and surrounding areas would have been swept along, deposited in fans and layers that can still be detected in the geological record. These deposits mark the path of the returning water, a kind of signature left behind by the force of the flow. One of the more intriguing questions about this moment is what it would have sounded and felt like over a wider area. The roar of the falling water near the gateway would have been intense, but the effects would have been felt far beyond that immediate zone. The sudden introduction of a massive body of water into the basin would have displaced air. potentially creating strong winds that radiated outward. The rise in humidity and the formation of clouds could have altered weather patterns across the region, at least temporarily. Rain might have fallen in areas that had been dry for long periods, adding another layer of change to the landscape and ecosystems. For animals on land, the advancing sea would have acted as a moving boundary. Plains that had served as migration routes or feeding grounds were cut off. Some creatures would have retreated to higher ground. Others might have been trapped by the rising water, forced to swim or find new paths. Birds, with their ability to move quickly and over long distances, may have been among the first to respond, shifting their routes to follow the changing shape of the land and water. For early human ancestors, if any were present in the region at the time, this would have been an event of enormous significance. The sudden loss of land bridges and the reappearance of a large body of water would have reshaped movement and access to resources. Routes that had been open for generations would have closed. New coastlines would have formed, offering different kinds of opportunities and challenges. But it's important to remember that this moment, as dramatic as it was, did not happen in isolation from everything that came before. The shape of the flood, the paths it followed, and the way it reshaped the basin were all influenced by the long dry phase. The deep valleys carved by rivers guided the flow of water. The salt layers influenced how the seafloor responded to the returning weight. The sediments laid down during the dry period were reworked into new features. In this way, the past and the present were woven together in the act of refilling. The idea of a sea returning in a rush can feel almost cinematic, like a scene from a story rather than a chapter in Earth's history. But the evidence for this kind of event lies in the rocks themselves. Geological formations near the western edge of the Mediterranean show signs of massive erosion and deposition that are difficult to explain with slow, gentle processes alone. Deep channels and large sediment fans point to a period of extremely high water flow. In the basin, the transition from thick salt layers to more typical marine sediments marks a sudden change in conditions, consistent with a rapid return of open water. These clues, scattered across the region and buried beneath layers of time, allow scientists to reconstruct the broad outline of what happened, even if the exact details remain a subject of ongoing research and discussion. There is also something deeply symbolic about this moment in the story. The basin, which had been defined by absence for so long, was now defined by presence. The quiet, inward-facing system of rivers, pools, and salt flats was replaced by an open, outward-facing sea connected to the global ocean. The Mediterranean, in a sense, rejoined the wider world. The water that rushed in carried not just salt and sediment, but also heat, nutrients, and life from distant places. It linked the basin back into the global circulation of the oceans, allowing it to participate once more in the exchange of energy and matter that shapes climates and ecosystems on a planetary scale. This reconnection would have had long-term effects on the region's climate. The presence of a large body of water moderates temperature, adds moisture to the air, and influences wind patterns. Over time, the return of the sea would have made the surrounding lands more temperate, and in some areas, more hospitable. Vegetation patterns could shift. New habitats would form along the reborn coastline. Marine ecosystems would develop and diversify as the basin settled into its new role as a sea once again. And yet, the Mediterranean that emerged from this flood was not a simple restoration of what had existed before. It was a new version shaped by the deepening of the basin, the presence of thick salt layers, and the reworked landscapes of the dry phase. Its salinity, its circulation patterns, and even its seafloor topography carried the imprint of what had happened during its absence. This is one of the quieter lessons of the moment the Atlantic broke through. Even dramatic returns do not erase the past. They build on it. The idea that a single opening could transform an entire region so quickly also highlights the importance of narrow, often overlooked features in shaping large systems. A strait, a channel, a low ridge of land can determine the fate of seas, and continents. In the Mediterranean's case, the narrow Western Gateway was both a point of vulnerability and a point of connection. When it closed, a sea disappeared. When it opened, a sea was reborn. This dual role continues today. The Strait of Gibraltar remains a narrow passage through which water flows in and out of the Mediterranean, maintaining its unique balance of salinity and circulation. It is a reminder that even now, the sea's relationship with the wider ocean depends on a relatively small and fragile connection. If you imagine standing at that strait in the present day, watching the surface waters of the Atlantic flow into the Mediterranean while deeper, saltier water flows back out beneath them, you are witnessing a quiet echo of a much more dramatic exchange that happened millions of years ago. The moment the Atlantic broke through was not just a flood, it was a re-establishment of a relationship between two bodies of water that had been separated for a very long time. As the basin filled, the roar of the initial flow would eventually soften. The waterfall would shrink as the difference in height between ocean and basin decreased. The torrent would become a strong current, then a steady exchange, and finally the layered flow we see today. The system would settle into a new balance, one that allowed the Mediterranean to remain a sea, but one that still carried the memory of its isolation in the form of higher salinity and unique circulation patterns. There is something quietly satisfying about this return to balance, even if it came through such a dramatic event. The basin, which had been shaped by absence, was now shaped by connection. The long silence gave way to movement. The weighting of rivers, salt layers, and scattered life gave way to a surge of water that tied the region back into the wider living network of the world's oceans. Let the image of that moment linger, a narrow barrier giving way, water rushing downhill with a force built up over hundreds of thousands of years, a vast empty basin filling, layer by layer, wave by wave, becoming a sea once more. It is a reminder that even the quietest, slowest changes can lead, eventually, to moments of transformation that reshape entire worlds in the space of a single unforgettable surge. If you were standing anywhere near the western edge of the Mediterranean basin at the height of the flood, the idea of a waterfall would feel almost too small to describe what you were witnessing. This was not a ribbon of water spilling gently over a cliff. This was an ocean finding a way downhill. The Atlantic did not arrive politely. It did not trickle in and test the ground. It surged forward, pulled by gravity into a space that lay far below its own surface, carrying with it the weight, momentum, and vastness of a connected global sea. The difference in height between the open ocean and the deep, empty basin was so great that the flow took on a character unlike anything we see on Earth today. To begin to picture it, imagine the tallest waterfalls you know. Perhaps you think of water dropping from a high cliff, breaking into mist as it falls, roaring as it crashes into the pool below. Now, take that image and stretch it sideways until it is no longer a single drop, but a wide, sprawling front of falling water. Then, imagine that this front is fed not by a river, but by an entire ocean. That is the scale we are dealing with. The opening between the Atlantic and the Mediterranean basin, once it gave way, became a channel for a volume of water that dwarfed every modern river combined. The flow rate, based on geological estimates, could have reached millions of cubic meters per second. For comparison, the Amazon, the largest river on Earth today, carries roughly 200,000 cubic meters per second at its peak. The flood into the Mediterranean may have been an order of magnitude greater. This was not just a stream. It was a moving wall of water guided by the shape of the land, accelerating as it dropped into the basin. At the point where the Atlantic spilled over the weakened barrier, the water would have plunged downward in a continuous thundering cascade. The height of this drop may have been several hundred meters, possibly more. That means the falling water had time to accelerate, to gain speed and force before it met the basin below. The impact zone at the bottom of this drop would have been a place of constant turbulence. Water crashing into water, air being pulled down and forced back up. Mist rising in thick clouds that could have been seen from far away. The sound would not have been a simple roar. It would have been a deep, layered noise, a combination of thunder, wind, and the low, continuous vibration of enormous volumes of water in motion. The ground near this zone would have felt alive, trembling under the force of the flow. Rocks and sediments would have been torn loose and carried away, reshaping the channel in real time. The waterfall was not just a feature of the landscape, it was actively building and destroying the landscape at the same time. As the water rushed into the basin, it did not spread out evenly like a calm tide. It followed the deepest paths first, pouring into the valleys carved by rivers during the long dry phase. These valleys became natural conduits, guiding the flood into the heart of the basin. Imagine a deep canyon that has been dry for thousands of years, its walls marked by layers of rock and sediment, its floor covered in salt and dust. Suddenly, a surge of water appears at its mouth. The front of the flood moves forward, not as a gentle wave, but as a fast-moving, rising wall. The water would climb the canyon walls as it filled the space, pushing air ahead of it, carrying debris, dissolving salt crusts, and smoothing sharp edges with sheer force. The canyon, which had once been a path for a single river, became a corridor for the sea itself. This pattern repeated across the basin. Valley after valley filled. Low points merged into growing lakes, which then merged into a single expanding body of water. The basin, which had been a patchwork of dry plains and scattered pools, transformed into a connected, moving system in a remarkably short span of time. The speed of this transformation is one of the most striking aspects of the event. While the drying of the Mediterranean unfolded over hundreds of thousands of years, the refilling may have occurred in less time than a human lifetime. Think about that contrast. Generations upon generations lived and died in a world where the sea was absent. The land adapted, life adjusted. The shape of the basin was carved and layered, and then, within a span that could be measured in years or even months, the sea returned and rewrote everything. The rising water level would have been noticeable almost immediately. Shorelines that had been far out on the basin floor began to move. Each day, the line between land and water crept higher up the slopes. Valleys that had served as travel routes or habitats were submerged. Salt flats disappeared beneath a growing reflective surface. From a distance, you might have seen the basin change colour. The pale, bright tones of salt and sediment gave way to the darker blues and greens of deepening water. The sky above, once reflected by dry ground, was now mirrored by a moving surface that caught and scattered light in a completely different way. The greatest waterfall on the planet was not a single static feature. It was a phase in a process. As the basin filled, the difference in height between the Atlantic and the Mediterranean gradually decreased. The drop became smaller. The force of the falling water lessened. The roar softened into a powerful current, then into a strong flow, and eventually into the layered exchange of water we see today. But during that initial phase, when the difference in elevation was at its greatest, the spectacle would have been unlike anything that has existed since. There is a temptation to imagine this as a single clean opening, a dramatic break where water suddenly burst through. The reality was likely more complex. The barrier may have failed in stages, with multiple channels forming and merging. The flow could have shifted from one low point to another as erosion reshaped the landscape. In some areas, water may have poured over ridges in wide sheets. In others, it may have cut deep, narrow gorges that focused the flow into concentrated torrents. The shape of the land at that moment played a huge role in determining how the flood behaved. This variability is written into the geological record. Sediment deposits near the western edge of the Mediterranean show signs of chaotic, high-energy processes. Layers of coarse material, mixed and jumbled together, suggest rapid movement and deposition. These are not the kinds of patterns you get from slow, steady currents. They point to something much more forceful. Farther into the basin, the incoming water would have slowed and spread out, dropping much of the sediment it carried. This created thick layers of material that blanket the salt deposits in many areas. These layers are another signature of the flood, a record of the moment when the basin shifted from a dry, mineral-dominated environment to a wet, sediment-rich one. The chemistry of the water during this phase would have been in constant flux. The Atlantic water entering the basin was less salty than the hypersaline water and salt flats it encountered. As it flowed over and into these areas, it dissolved large amounts of salt, increasing its own salinity. This process happened on a massive scale. The returning sea did not simply cover the salt, it interacted with it, reshaping its own composition in the process. This is part of the reason the Mediterranean remains saltier than the Atlantic today. The legacy of its dry phase is still present in the water itself. The mixing of waters also had implications for temperature and circulation. The incoming Atlantic water would have been cooler and denser in some seasons, warmer and lighter in others, depending on global climate patterns at the time. As it mixed with the basin's remaining waters, it created complex flows, with layers of water moving in different directions and at different depths. These early circulation patterns would have influenced how quickly the basin filled and how evenly the water spread. They would also have shaped the initial distribution of nutrients and organisms in the reborn sea. Life, once again, was caught in the middle of a dramatic change. Organisms adapted to the extreme salinity of the basin's remaining pools suddenly found themselves in a more moderate environment. Some may have thrived, expanding their range as the water spread. Others may have struggled, unable to compete with species arriving from the Atlantic or to adjust to the new conditions. Plankton, carried in by the flood, would have spread rapidly, forming the base of new food webs. Fish and invertebrates followed, either swimming in through the newly opened gateway or emerging from refuges within the basin. The rebirth of the sea was not a gentle reintroduction of life. It was a rapid blending of ecosystems, a meeting of organisms that had been separated for a very long time. This kind of mixing can lead to bursts of diversity as new interactions and niches emerge. It can also lead to competition and loss, as some species are outcompeted or fail to adapt. The greatest waterfall on the planet was, in this sense, not just a physical event. It was a biological one. It reshaped the living world as much as it reshaped the land. There is also an atmospheric dimension to this moment that is easy to overlook. The sudden introduction of a massive body of water into a dry basin would have changed the air above it almost immediately. Evaporation from the new sea surface would have added moisture to the atmosphere. Clouds could form more readily. Rainfall patterns might have shifted, at least locally. The basin, which had been defined by dry air and extreme temperature swings, began to develop a more moderated climate. These changes would have affected the surrounding lands as well. Vegetation patterns could shift as new sources of moisture became available. Rivers might respond to changes in rainfall, altering their flow and sediment load. The return of the sea was not just a flood, it was the reintroduction of a major climate system into the region. One of the more intriguing aspects of this event is how it might have been experienced from different vantage points. Near the Western Gateway, the sound and movement would have been overwhelming. Farther into the basin, the change would have been more gradual, though still rapid on a geological timescale. If you were standing in the middle of the basin, perhaps near one of the remaining pools of water, you might first notice a change in the air, a rise in humidity, a shift in the wind. Then, in the distance, a dark line on the horizon where water was advancing across the plains. Over days or weeks, that line would move closer. The ground beneath your feet might grow damp as the water table rose. Small streams could form where none had existed before, as the rising sea pushed groundwater upward. Eventually the water would arrive, spreading across the surface, merging with the pool you had been standing beside, and transforming a small, isolated body of water into part of a vast connected sea. This kind of perspective highlights how the same event can feel very different depending on where you are. For some, it would have been an immediate dramatic spectacle. For others, a steady, almost quiet transformation. The greatest waterfall on the planet in this sense was both a singular, intense phenomenon and a distributed process that played out across an enormous area. There is also something deeply humbling about the scale of energy involved. The potential energy stored in the difference in height between the Atlantic and the Mediterranean basin had been building for hundreds of thousands of years. When it was released, it powered a flow of water that reshaped landscapes, ecosystems, and climate. This is a reminder that the Earth operates on timescales and energy levels that far exceed our everyday experience. The forces that seem gentle or slow, like the movement of tectonic plates or the accumulation of salt, can set the stage for events of extraordinary intensity. And yet, even this intensity is part of a larger cycle. The greatest waterfall did not mark the end of the story, it marked a transition. As the basin filled, the dramatic drop that created the waterfall became smaller. The flow softened. The system moved toward a new balance, one where water could move in and out of the Mediterranean through the narrow western gateway without overwhelming the landscape. The waterfall became a strong current. The current became a layered exchange. The roar became a steady, persistent movement that continues to this day. The Mediterranean, once again, became a sea, but it was not the same sea that had existed before the long dry phase. Its basin was deeper. Its seafloor was shaped by thick salt layers and reworked sediments. Its salinity was higher. Its circulation patterns were unique. The greatest waterfall had not just filled a hole in the land. It had created a new version of a familiar world. If you stand by the Mediterranean today, watching waves roll in and out, it can be difficult to imagine the scale of what once happened here. The water looks calm, the horizon looks stable, the connection to the Atlantic seems narrow but steady. And yet beneath that calm surface lies the memory of a time when this narrow connection became the site of one of the most powerful flows of water the planet has ever seen. There is something quietly moving about that contrast. The idea that a place defined today by gentle beaches, busy ports, and slow-moving currents was once the scene of a flood that reshaped an entire region. It invites a different way of seeing familiar landscapes, not just as they are, but as they have been, and as they might be again under different conditions. The greatest waterfall on the planet is not something you can visit or photograph. It exists in the layers of rock, in the shape of the seafloor, and in the chemistry of the water itself. It exists as a moment in a long story, a point where slow, quiet processes gave way to rapid, dramatic change. Let the image of that immense flow linger. An ocean spilling into a deep basin, water falling, surging, spreading, land being reshaped in real time, the sound of movement echoing across a landscape that had been quiet for so long. Even in the slow, patient rhythms of the earth, there are moments when everything seems to move at once, when the balance tips and the world quite literally pours itself into a new shape. The water did not stop moving just because the basin was full again. Even after the last dry valleys disappeared beneath the rising surface and the roar of the great flood softened into a steady exchange between ocean and sea, the Mediterranean continued to change. What had returned was not a simple restoration of an old world. It was the beginning of a new one, shaped by everything that had happened during the long absence of water, and by the powerful way that water came back. Imagine the basin in the first years after the flood. The surface would have been restless, not yet settled into the familiar patterns of currents and tides we see today. The water carried the memory of its violent entry in the form of suspended sediments, clouds of fine particles that drifted through the depths, slowly settling onto the seafloor. These particles came from everywhere, from the eroded western gateway, from the walls of deep river valleys that had been scoured as the sea rushed in, from the salt flats and plains that were dissolved and swept away. The water itself was a moving archive, carrying pieces of the landscape within it. As this material settled, it began to reshape the floor of the basin once again. Thick layers of mud and sand blanketed the salt deposits, smoothing sharp edges, filling small depressions, and creating a more continuous surface for marine life to inhabit. In some places, the deposits formed gentle slopes. In others, they built up into underwater ridges and fans that altered how currents flowed. The seafloor, like the land above it, became a place of subtle variation rather than a single uniform plane. One of the most important changes during this phase was the re-establishment of circulation. The Mediterranean did not simply fill and then sit quietly. The narrow connection to the Atlantic created a constant movement of water. Less salty Atlantic water flowed in at the surface. Saltier, denser Mediterranean water flowed out at depth. This layered exchange became the heartbeat of the reborn sea. It brought in fresh water, oxygen and nutrients from the wider ocean. It carried out excess salt and heat. Over time, it helped stabilize the chemistry and temperature of the basin. But this circulation was not identical to what existed before the dry phase. The deeper basin, shaped by subsidence and salt movement, created new patterns of flow. Some areas became zones of strong currents. Others became quieter pockets where water moved slowly and sediments could accumulate. These differences mattered for life. Marine organisms respond closely to the movement of water. Currents carry food, larvae, and chemical signals. They shape where plankton blooms form and where fish schools gather. They influence where reefs can grow and where soft-bottom communities take hold. In the reborn Mediterranean, these patterns had to be built from scratch. Plankton, the tiny drifting organisms that form the base of marine food webs, were among the first to spread widely. Carried in from the Atlantic and growing in the nutrient-rich waters of the basin, they created clouds of life that could be seen as faint colour changes in the water. Where plankton thrive, other life follows. Small fish and invertebrates fed on them. Larger predators followed the smaller ones. Over time, a complex web of interactions began to form, linking organisms across different depths and regions of the sea. The coastline too was transformed. The rising water did not simply create a smooth, even edge between land and sea. It interacted with the varied shape of the land that had been exposed during the dry phase. Deep river valleys became long, narrow inlets. Broad plains turned into shallow coastal shelves. Steep slopes formed dramatic underwater drop-offs just beyond the shoreline. These features created a wide range of coastal environments. Some areas had gentle beaches and lagoons. Others had rocky cliffs that dropped straight into deep water. These differences provided niches for many different kinds of life. Plants that could tolerate salty water, like early forms of seagrasses, found places to take root in shallow, sheltered areas. These plants helped stabilize sediments and created habitats for small animals. Shellfish and other invertebrates attached themselves to rocks and hard surfaces. Fish found shelter among underwater ridges and in the shadowed spaces of submerged valleys. The return of the sea also changed the relationship between land and water in more subtle ways. The presence of a large body of water influences the climate of the surrounding region. It moderates temperatures, making summers less extreme and winters milder. It adds moisture to the air, increasing the likelihood of clouds and rain. Over time, this shift would have altered vegetation patterns on land. Areas that had been dry and open during the basin's isolation might have become greener. Rivers might have responded to changes in rainfall, adjusting their flow and sediment load. This, in turn, affected the sea. Rivers carry nutrients and organic material into coastal waters, fueling plankton growth and supporting productive ecosystems. The reborn Mediterranean began to develop the familiar pattern of rich coastal zones and less productive open waters. One of the quieter but important changes during this period was the way the salt layers beneath the seafloor continued to influence the basin. The weight of the returning water pressed down on the crust, causing further subsidence in some areas. The salt, soft and mobile, responded by flowing slowly, forming domes and ridges that subtly reshaped the seafloor over long periods. These movements could change the depth of certain regions, alter current pathways, and influence where sediments accumulated. In this way, the ancient salt deposits formed during the dry phase remained active participants in shaping the reborn sea. The idea of a world being reshaped does not only apply to the physical landscape, it also applies to the connections between regions and eventually to human history. The Mediterranean's return as a sea re-established a major barrier and a major pathway at the same time. On one hand, the water separated land masses that had been connected by dry plains and valleys. On the other, it created a navigable route that would later become one of the most important corridors for trade, travel, and cultural exchange in the world. But even before humans began to use it in that way, the sea influenced the movement of animals and plants. Species that could cross water or follow coastlines spread differently than those that relied on land bridges. Over time, this helped shape the distinct ecological regions around the Mediterranean basin. Some species that had moved freely across the dry basin during the isolation period now found themselves separated by water. Their populations became isolated again, potentially diverging into new forms. Other species, especially those adapted to marine or coastal environments, found new opportunities to expand their range. This back and forth between connection and separation is a recurring theme in the Mediterranean's long history. The basin has alternated between being a bridge and a barrier, a meeting place and a dividing line depending on the balance between land and water. The sea that was reborn after the flood carried that dual role forward. There is also a sense in which the Mediterranean became a kind of memory bank for its own transformation. The layers of sediment on the seafloor recorded the return of water. The chemistry of the water retained the signature of dissolved salt from the dry phase. The shape of the coastline and underwater landscape preserved the outlines of ancient valleys and plains. These records allow scientists today to reconstruct what happened, to read the story of disappearance and return written in rock and water. But beyond the scientific record, there is a more reflective way to think about this reshaping of the world. The basin spent hundreds of thousands of years as something other than a sea. For all that time, the idea of a vast connected body of water might have seemed almost unimaginable to any creature living there. The landscape was defined by land, by salt, by isolated pools and deep valleys. Then, in a relatively brief moment, everything changed. The defining feature of the region became water again. This kind of transformation challenges the way we think about permanence. It reminds us that what feels stable and enduring on a human timescale can be temporary on a geological one. The Mediterranean we know today, with its familiar coastlines, islands and currents, is not a fixed entity. It is a phase in a long sequence of changes, shaped by forces that operate far beyond our everyday experience. The reborn sea also carried forward the legacy of its isolation in the form of its unique properties. Its salinity remains higher than that of the Atlantic. Its circulation patterns are distinct. Its ecosystems have their own character, shaped by the semi-enclosed nature of the basin and its narrow connection to the open ocean. These features make the Mediterranean a kind of natural laboratory, a place where the interactions between ocean, land and atmosphere play out in a more concentrated and visible way than in many other parts of the world's oceans. The reshaping of the world around the reborn sea extended to the way the region interacted with global climate systems. The presence of a large body of water in a mid-latitude region influences atmospheric circulation. It can affect the path of storms, the distribution of rainfall, and the movement of heat between the tropics and higher latitudes. Over long periods, these effects can influence the climate of entire continents. The Mediterranean, in this sense, became not just a local feature, but a participant in a global system. There is also a quieter, more personal way to connect with this story. If you have ever stood by the Mediterranean today, you may have noticed how the sea feels different from the open ocean. The waves are often smaller. The water can be warmer near the surface. The coastline can change quickly over short distances, from sandy beaches to rocky cliffs to sheltered coves. These qualities are part of the sea's identity as a semi-enclosed basin, shaped by its narrow connection to the Atlantic and its complex underwater landscape. Knowing that this sea was once absent, once replaced by a vast dry basin of salt and dust, can add another layer of depth to that experience. It can make the sound of waves and the smell of salt in the air feel like part of a much longer story. The rebirth of the sea was not the end of change. The crust beneath the basin continued to move. The salt layers continued to flow slowly. Sediments continued to accumulate. The narrow gateway at the west continued to be shaped by currents and erosion. All of these processes mean that the Mediterranean is still, in a very real sense, a work in progress. Future changes, on timescales far beyond our own, could alter it again. Sea levels could rise or fall. Tectonic movements could reshape its boundaries. Connections to other bodies of water could change. The story of disappearance and return is not necessarily a one-time event in the planet's history. It is part of a broader pattern of transformation that has played out many times in different forms across the Earth. The idea of a sea being reborn also invites a different way of thinking about resilience. The basin did not simply recover from its dry phase, it was transformed by it. The new sea carried forward the imprint of what had happened, in its depth, its chemistry, its circulation, and its landscapes. In that sense, rebirth does not mean a return to a previous state. It means the creation of something new from the materials and experiences of the past. This is a theme that resonates beyond geology. Systems, whether natural or human, often do not revert to exactly what they were after a period of disruption. They adapt, reorganize, and emerge in a different form. The Mediterranean story is a large-scale example of that process. As the reborn sea settled into its new role, it became a place of interaction. Rivers delivered water and sediment from distant lands. Winds carried dust and moisture across its surface. Currents connected it to the Atlantic and through that connection to the rest of the world's oceans. Life in the sea and around its shores became part of a dynamic, interconnected system that spanned continents and climates. Over millions of years, this system would influence the development of ecosystems, the movement of species, and eventually the paths of human societies. But at this stage in the story, it is enough to hold on to the image of a basin filled once more, not just with water, but with possibility. The salt flats are gone, buried beneath layers of sediment and sea. The deep valleys are now underwater channels. The scattered pools have merged into a vast, connected body. The world around the Mediterranean has been reshaped, both physically and in the relationships between land, water, air, and life. There is a sense of quiet completion in this phase, but not finality. The sea has returned, but the processes that shaped its absence and its rebirth continue. The crust still moves, the salt still flows, the water still circulates in and out of the narrow western gateway. The story, in other words, is still unfolding. For now, let the image of a reborn sea rest in your mind. A basin that was once empty, now filled. A landscape that was once defined by salt and dust, now shaped by waves and currents. A world that has been reshaped, not erased, by the return of water to a place that waited for a very long time to become a sea again. Long after the salt settled, long after the floodwaters softened into familiar waves and steady currents, the Mediterranean began to speak in a quieter way. Not through dramatic changes in its surface or sudden shifts in its coastline, but through subtle hints, gentle patterns, and small reminders woven into the land, the water, and even the way people study and move through the world today. The vanishing sea does not announce itself loudly anymore, it whispers. Those whispers are first found in the rocks. Along cliffs, road cuts, and mountain slopes around the Mediterranean, you can see layers that seem out of place if you only think in terms of the present. Bands of white and pale grey, thick deposits of salt and gypsum appear far above modern sea level. They sit in hillsides and valleys, sometimes exposed by erosion, sometimes revealed by construction or drilling. To someone passing by, these layers might look like just another part of the landscape. To someone who knows what they are a message from a time when the sea was not here at all. Each of those layers represents water that evaporated, leaving its minerals behind. Each one is a quiet record of a moment when the balance tipped toward dryness instead of abundance. Together they form a timeline of loss and return, written in stone rather than in words. Beneath the water itself, the whispers continue. The Mediterranean seafloor is not a smooth, featureless plain. It is shaped by deep basins, ridges and slopes that reflect the history of subsident salt movement and sediment deposition that took place during and after the dry phase. Modern mapping of the seafloor, using sonar and deep-sea instruments, reveals shapes that mirror the ancient landscape. Submerged valleys trace the paths of rivers that once flowed across dry ground. Subtle rises mark the locations of salt domes that have slowly pushed upward from below. When scientists look at these maps, they're not just seeing the present sea floor, they are seeing a layered story, a record of how a vanished sea still influences the one that exists today. The water itself carries a whisper of the past in its chemistry. The Mediterranean is saltier than the Atlantic. This is often explained by the modern balance between evaporation and the limited inflow of fresh water through the narrow western gateway. But there is also a deeper legacy at work. The basin is built on thick layers of salt left behind by its disappearance. As water moves through and over these deposits, small amounts of minerals dissolve and re-enter the sea. The past, in a very literal sense, continues to flavour the present. This extra salinity affects how water circulates. Denser, saltier water sinks more readily, driving deep currents that flow out of the Mediterranean and into the Atlantic beneath the surface. This layered exchange is part of a larger system of ocean circulation that helps move heat and nutrients around the planet. In that way, the story of a vanishing sea is not confined to one region. It is connected to global processes that influence climate far beyond the Mediterranean shores. The whispers are also found in the shape of the coastline. The Mediterranean's edges are complex, full of inlets, peninsulas, islands and narrow straits. Some of this complexity comes from tectonic activity, the slow collision and separation of pieces of crust, but some of it reflects the legacy of ancient valleys and plains that were reshaped when the sea returned. Long, narrow bays often follow the paths of former river valleys. Broad shelves mark areas that were once flat, low-lying land. Steep underwater slopes can indicate places where the basin floor dropped away sharply during the dry phase. These features influence everything from where fish gather to where people build harbours. They shape patterns of waves, currents and sediment movement that affect coastal erosion and beach formation. So when a fisherman chooses a spot or a city plans a port, they are, in a small way, responding to the shape of a world that was defined by the absence of water millions of years ago. There is another kind of whisper in the way scientists think about change itself. The Messinian Salinity Crisis, as this period is often called, challenged long-held assumptions about how stable large bodies of water are. For a long time, it was difficult to imagine that a sea as large as the Mediterranean could nearly disappear. The discovery of thick salt layers beneath the seafloor forced a rethinking of what is possible on a planetary scale. It showed that relatively small changes in geography, like the uplift of a narrow land bridge, can have enormous consequences. This idea has influenced how scientists look at other parts of the world. enclosed or semi-enclosed seas, large lakes, and even polar ice sheets are now studied with an awareness that their stability can be more fragile than it appears. The whisper here is not about the Mediterranean alone. It is about the sensitivity of Earth's systems, about how interconnected processes can amplify small shifts into major transformations. There is also a message for how we think about time. The disappearance of the Mediterranean unfolded over hundreds of thousands of years. The return of the sea may have happened in a span short enough to fit within a human lifetime. The contrast between these two timescales is striking. It reminds us that slow, almost invisible changes can build up to moments of rapid transformation. That what feels steady and permanent can, under the right conditions, change very quickly. This perspective has found its way into discussions about modern environmental change. While the causes and contexts are very different, the basic lesson about accumulation and tipping points resonates. The vanishing sea, in this sense, whispers a cautionary note about assuming that large systems are immune to disruption. But the whispers are not only warnings, they're also stories of resilience and adaptation. Life did not vanish when the Mediterranean did. It adjusted. It moved into new spaces. It found ways to persist in pockets of water, in river valleys, in salt-tolerant communities. When the sea returned, life adjusted again. New ecosystems formed. Old ones were reshaped. The basin became a place of mixing, where organisms from different regions and histories came together. This pattern of loss, persistence, and renewal is a recurring theme in Earth's history. The Mediterranean story is one example among many, but it is a particularly clear and well-preserved one. For people who live around the sea today, these whispers can be felt in more personal ways. The Mediterranean has long been a crossroads of cultures, a place where ideas, goods, and people move between continents. Its role as both a barrier and a bridge has shaped history for thousands of years. In a deeper sense, this role echoes its geological past. The basin has alternated between connection and separation, between openness and isolation. These shifts, whether driven by water or by human movement, have created a region defined by interaction. Standing on a modern shoreline, watching ships pass through narrow straits or ferries, cross between islands and mainland, you're witnessing a continuation of that theme. The sea connects, even as it divides. There is also a quiet presence of the past in the way the land around the Mediterranean feels. The climate, with its warm summers and mild, wetter winters, is shaped by the presence of a large body of water. The vegetation, from olive trees to coastal grasses, reflects this balance of moisture and heat. This environment exists because the sea returned. Without it, the region might look and feel very different, perhaps closer to a vast, arid basin than the varied landscapes we see today. So when you walk through a coastal town or hike along a cliff overlooking the water or sit by the shore at sunset, you're experiencing a world that owes its character to a dramatic change that happened millions of years ago. The whispers are also present in the tools and methods scientists use to explore the planet. Techniques developed to study the Mediterranean's salt layers and seafloor structures have been applied to other regions. They help researchers understand ancient climates, the movement of continents, and the history of other vanished seas and lakes. In this way, the Mediterranean story has become part of a larger conversation about Earth's past, informing how we interpret clues from around the world. There is something quietly powerful about that. A single region's transformation contributing to a global understanding of how the planet works. The whispers even reach into the way we imagine the future. While the exact conditions that led to the Mediterranean's disappearance are not likely to repeat in the same way, the idea that large bodies of water can change dramatically remains relevant. Sea levels rise and fall over geological time. Tectonic movements continue. Climate shifts alter patterns of evaporation and precipitation. The Mediterranean itself will not remain exactly as it is forever. Its boundaries, depth, and connection to the Atlantic will continue to evolve, even if those changes are far beyond the scale of human lifetimes. Thinking about the vanished sea can encourage a broader, longer view of the world, one that extends beyond immediate concerns and into the deep past and distant future. There is also a more subtle, almost philosophical whisper in this story. The idea that a familiar, defining feature of a region, like a sea, can disappear and then return challenges how we think about identity and continuity. The Mediterranean today feels like an enduring presence. It has been central to human history for thousands of years. It shapes the culture, economy, and imagination of the people who live around it. And yet, in the longer story of the planet, it is a relatively recent and changeable feature. This does not make it less meaningful. If anything, it adds a layer of depth. The sea's presence becomes something to appreciate not just for what it is, but for the fact that it exists at all, shaped by a series of events that could have unfolded differently. The whispers of the vanished sea invite a kind of attentiveness, a way of looking at landscapes and waters not just as static backdrops, but as dynamic participants in a long ongoing story. They encourage noticing the small details, a line of rock in a hillside, a change in the colour of the water near a salt spring, the shape of a bay that seems to mirror the curve of a river valley. Each of these can be a quiet hint of what came before. There is also something to be said about how this story influences our sense of scale. Human history, for all its complexity and drama, occupies a very small slice of the timeline that includes the disappearance and return of the Mediterranean. Civilizations rose and fell long after the sea had settled into its modern form. This perspective can feel humbling. It places our own stories within a much larger context, one where mountains rise and erode, seas vanish and return, and the planet continues its slow, steady transformation. At the same time, it can be grounding. It reminds us that change is a constant, not an exception, that stability is often temporary, that resilience and adaptation are as much a part of the world as permanence and tradition. The whispers of the vanished sea are not loud or insistent. They do not demand attention. They are there for those who are curious enough to listen. They can be heard in the way waves move through a narrow strait, in the way salt crystals form on a rock near the shore, in the way scientists talk about layers of sediment and ancient climates. They can also be felt in the simple act of sitting by the water and letting your mind wander. If you pause for a moment and imagine the place you're in, whether it is near the Mediterranean or far from it, you can think about what lies beneath the surface, not just in a physical sense, but in a historical one. Every landscape has a story layered beneath it, rivers that once flowed in different directions, forests that once stood where cities now rise, seas that once filled basins that are now dry plains. The Mediterranean story is one of the more dramatic examples, but it is part of a broader pattern that applies everywhere. The vanishing sea still whispers to us today by reminding us that the world we see is not the only world that has existed in this place. It is one version among many, shaped by forces that operate far beyond our immediate perception. There is a certain calm that can come from holding that idea. Not a calm that dismisses the importance of the present, but one that places it within a wider frame. One that recognizes both the fragility and the resilience of the systems that support life and shape landscapes. As this gentle journey reaches its resting point, the Mediterranean stands as it does now, full of water, alive with currents, bordered by lands that have been shaped by its presence. But beneath that familiar surface lies the memory of absence. Beneath the waves, layers of salt and sediment carry the record of a time when the sea was gone. The whispers of that time are still there, in the chemistry of the water, in the shape of the seafloor, in the patterns of life and climate that define the region. They do not speak in a single, clear voice. They speak in many small ways, scattered across disciplines and experiences, waiting to be noticed. And perhaps that is the most fitting way for such a story to endure. Not as a loud reminder of dramatic change, but as a quiet presence that adds depth to the world we move through every day. The Mediterranean, in this light, becomes more than a sea. It becomes a living record of transformation, a place where absence and return, loss and renewal are woven together in layers of rock, water, and time. If you ever find yourself near its shores, you might let that thought settle for a moment. The sound of waves, the warmth of the air, the scent of salt. And beneath it all, the soft, persistent whisper of a world that once was, and the long, patient story of how it became the world you see now.